Right, hello everyone, and welcome to this GNOSIS Sandpit on Precision SSA. So it's great to see so many of you here with us today, and I know that quite a few people are joining us from across the globe. So thank you for joining us at, I'm sure, less favourable hours. So the purpose of this event today is to follow on from a workshop that was held in July 2020. Quite a successful workshop in the end, despite it being fully virtual. It was one of the first fully virtual events that we held after the start of the pandemic. And today we hope to essentially further the discussions that were had at that time, and also hopefully inspire some collaborative ideas to take advantage of GNOSIS funding opportunities. So keep that in mind as we go throughout the day. If you do have a good idea, then there are plenty of opportunities available to take advantage of. So my colleague Stuart Eves and our program manager will be giving a much more in-depth presentation on those funding opportunities at the end of the day. But just to act as a quick prelude. Oh, sorry, we've got someone unmuted. If we could all make sure that we mute if we're not speaking, please. Just a second. Okay, that should be quiet now. So yes, if anybody's got any questions on those funding opportunities as we go through, please don't hesitate to get in touch with me via the chat or ask questions as we go. So yes, we're happy today to be joined by Luke Cornwell, who's actually one of the recipients of some of these GNOSIS funding opportunities, namely via the PhD studentship that we offer part funding for. So I'm going to hand over to Luke shortly. I'll need to share his slides for him, so I'll stop sharing this now, and then I'll come back to the logistics for the day afterwards. So Luke, you're there, that's great. Just bear with me while I share. Okay. Is that looking okay?
I don't have my slides on my screen from what I've seen.
Hang on a sec.
That's better. Yeah, let's brought them up.
Yeah, is that good? Okay, there you go. Over to you, Luke. Thank you.
I'm very glad we sent these preliminary ones out to you previously, because I'm in the middle of a technical situation with my PC, so I'm unfortunately had to join by my phone. But thank you very much for the lovely introduction there, James. As James has just said, I am recipient of a funding for my studentship for my PhD. So I'm co-funded by obviously GNOSIS and the University of Kent, for whom I'm doing my PhD with. And my research is in the development of space dust and orbital debris detectors. Could you move on to the next slide? I'm not sure what's in this version.
There you go.
But yeah, so why the research, or why my research? And well, one of the key questions within SSA, also Space Situational Awareness, with regards to orbital debris, is to make an accurate model of the debris environment, or the near Earth debris environment. And to do that, we need to kind of gather data sets which will actually inform these models, and from which we can base our models and predictions upon. And to collect those data sets, there are a number of different methods. But for your smaller objects, especially the millimeter size kind of debris and orbital debris range, the only real way of doing that is to actually characterize the debris itself, which I believe we'll hear a lot more from Thomas later on today, via in situ detection. And that's using either active or passive detectors. So that's where I come in. My research is in developing these detectors that we can actually put into space to characterize the near Earth dust population, and then from that we can determine these data sets, which will then inform our debris environmental models. Okay, so one of the particular detectors that I'm currently working on developing is NASA's Orbital Debris Programs Office's DRAGONS detector, which is a time of flight style detector, which you can see a kind of prototype of in the bottom image here. And that works by basically using the time and location of impact on 2 separate Kapton films, which you can see here. It's like the yellow films on the prototype detector in the image, and from that, from the time of detection and the location of detection, we can then infer or determine the trajectory and speed of the incident particle, and so that will allow us to then map out the orbits which these particles are within, and then that again plays back into trying to determine what is in space, what debris is up there, and how fast it's traveling, which would then infers kind of how much damage it would do.
چیزه کنفرم
Thank you very much, James. So what was I? Sorry. Yes. So yeah, from knowing the orbits and the orbital speed of the debris, we can then infer the kind of damage that it will produce on impact with different spacecraft and so forth, which again in turn allows us to determine our optimal spacecraft shielding and generally get a better idea for the sustainability in space itself. So up until now, for my first year, because I'm now in my second year of my PhD, for my first year, it was spent producing a prototype of the Dragon's detector, which you can see, as I said, in that bottom image there. And since then, I've been using the University of Kent's impact facility to hypervelocity impact test said prototype. And we have determined that, it has proven that this prototype provides accurate measurements of speed, of the incident particle speeds, to within 1%. And so that was work we did last year. And now going forwards, we intend to look at different projectiles or different debris analogs, as it were, of different sizes, different compositions, to determine the effects of the penetration or film penetration on those particles, to then determine what would occur to the particle as incident upon the detector in space, and use it as a calibration data set to then determine what the particle looked like before interaction with the first film. So obviously for very small projectiles, past research has shown that they are likely to undergo deceleration and or disruption, and that's obviously what's motivated this kind of big key question, and why we need calibration data to, as I said, look at what we receive if we have a speed of, say, 2 kilometers per second, or more likely 6 or 7 kilometers per second. Was that the speed of the incident particle, or was that the speed of the particle after penetration, now that it's been decelerated by, say, 2 kilometers per second? Because there's quite a big difference between an 8 kilometer per second impact and 6 kilometer per second impact with regards to energy, and therefore devastation and so forth to your satellite or spacecraft. So that's the future goals. We're going to look at the different kind of effects that our detector actually has upon the detections and the data that it collects. So yeah, the data I'm collecting currently will act as calibration data and hopefully inform the future design of Dragons. And yeah, that's a brief overview of kind of my research, where it's at now, and how it fits into the whole overall SSA. If there's time for any questions, James, I'm more than happy to answer a few.
Thank you very much for that, Luke. And as Luke said, if there are any questions, please raise your hand. Alternatively, if Luke's happy to stick around and sticking around for the day, do sort of send messages directly in the chat to him if you have any questions that you think of later on. But yeah, that was really interesting, Luke, and I'm sure a lot of that research with several implications for the various topics we'll be discussing throughout today. So it's really good addition to the introduction, I think, and nice to see that GNOSIS funds are being put to good use. So yeah, thank you very much for that.
Great, thank you very much, James. And yes, I will be around all day, so I'll be able to answer any questions in chat and or directed.
Brilliant.
I think I saw one pop up in the chat. Sorry, I'm on my phone, so I have to try and go there and find it.
I think that might be about the muting, actually. But yeah, I'll come back to that if we have time. But yes, I'll stop sharing that now, Luke, and head on to the program for the day.
Check for it later.
Thanks, Luke.
Thank you.
So let's just find the program now. So we've got that there. Okay. Whoops. Okay, can everybody see the program okay there? So I didn't hear anybody reply.
Yes, that's fine. You can
brilliant. Thank you. Cheers. Thank you. So yes, just to go through a few logistics for the day before we begin. So yes, if we could try and keep muted when not speaking, that would be really helpful. Just because background noises can distract people who are talking. But yeah, if we try and ensure that's adhered to. And then if we have any questions throughout the day or discussions points, then please don't hesitate to raise your hand, and I'll invite you to the floor when there's an appropriate time for questions. Yes, please also feel free to use the chat. I can pass on questions if you'd prefer via the chat, and obviously if there's a talk ongoing, it might be easier to put it in the chat for us to get to afterwards. So yes, that's all the logistics. I think we'll be doing Q&As as we go. So hopefully there'll be time in each speaker's slot to answer a few minutes of questions, and then we'll have discussion or more general discussion at the end of each block of the day. So we've got the program here for the first half of the day. So I'll keep that up until I switch over to the first speaker for you to digest. But yes, just to move on to the main program then, I'll introduce the first speaker, which is Jeremie Houssineau from the University of Warwick, a member of our new Centre for Space Domain Awareness. And he'll be talking to us about opportunities and challenges of a faithful representation of uncertainty in SSA. So thanks for joining us, Jeremie, and looking forward to your talk. I'll hand over to you.
Thank you. Okay. So since we're apparently on the day of computer issues, apparently my bandwidth is a bit low, so I hope I'll come clear, but if there's any issue there, please let me know. So, all right. So yes, thank you for the introduction and thank you for the invitation. So I'll jump right in if I can. Yes. So first I'll talk about actually kind of the main part of my work, which is about modeling uncertainty in a different way, and I call this deterministic uncertainty. Well, I'll tell you a bit more about this, and then I'll also present some results in multi-target tracking, which is kind of the other focus of my work, and I work at basically at the intersection of those two areas. And then I'll move on to SSA and what are the kind of opportunities and challenges there. I couldn't help myself but put some equations in the slides. If I'm not even going to define all the terms, so those equations are really, you can consider them as pictures, and it's more like as a support to explain the ideas. All right, so let's talk a little bit about uncertainty. So we use, people use probability distributions to model basically everything. As soon as you're uncertain about something, people put probability distribution on it, which is fine in many cases, but there are some issues with doing that, in particular when we don't know anything and when we don't know much. And so the technical term for this is improper priors, but basically the idea is that if you're, for instance, on the real line or in some Euclidean space and you know nothing, then to model that with a probability distribution, you actually have to use something that is not a probability distribution. And so that already shows some of the limitations of this approach. Combining information can also be difficult with probability distribution. There are some ways to do it, but it's not very natural. And so again, that's something that goes a little bit against our own intuitive interpretation of information as something that we can share and combine and sort of learn from easily together. And the last thing actually is that you can get some counterintuitive results. And for this, I'll use this picture from this paper by Emmanuel Delande, Moriba Jar, and Brandon Jones. I think Moriba is here today, so hello. Here we have basically an analysis for probability of collision. And so what we'll be most interested in at first is the dashed line. And so the idea here is that if you look at the uncertainty you have about, let's say, one object, you know the position of one object, and but you don't know the position of a second object, and you're interested in evaluating the probability of of collision between those two objects. Then you have to, if you use probability distribution, what you'll notice is that the more uncertain you are about the position of the object, and basically the general trend is the lower the probability of collision will be. And that makes perfect sense if the position of that object was indeed random, right? So the larger the space, the larger the uncertainty, the lower the probability of being at a specific point. But that's not exactly what we want. And we can compensate for that by introducing some ideas of risk, or basically introducing additional concepts on top. But usually you might have problems of calibration with that, and it's not quite that intuitive. So I think what would be intuitive is maybe not to have probability, but to have something else, and to think basically here in terms of possibility. And the idea is that what we would want is something that increases. So the possibility that there'll be a collision will increase when I have more uncertainty. And in the limit case, if I know nothing, then I shouldn't be able to rule out a collision. But what I would want to conclude is that maybe I don't have information, I don't have enough data. And that's what we want to achieve. We want to, in the case where we know nothing or we know very little, then the possibility of collision should be 1. We have no information against a collision happening. And maybe we want to collect more information. So how to do this? Very generally, if we think about a parameter that is fixed, that we don't know it and we'd like to learn it. So the important ingredients here are basically what I call an uncertain variable. That's the analog of a random variable. And that's really just saying, well, we have some object that is not fixed, but in a sense that we don't know it. And for different true state of natures, we have different values of that parameter, but we don't know which one is true. As opposed to a random variable, we don't have any probability structure on omega, on the sample space. We just know something about the value of that parameter in the parameter space directly. And so to describe that, we use a possibility function, which is positive, like a probability distribution, but instead of having sum or integral equal to 1, it has maximum 1. And it's really this idea of saying in the worst case, we know nothing, then it's kind of everything is possible, everything is equal to 1. And so that's exactly the example I have here. So if I put the function to be equal to 1 everywhere, then everything is possible. There's nothing I can rule out. I have information about. I have no information at all. And so that's already one aspect. I can model the total absence of information. So it's a completely different thing from a probability distribution. So in a sense, we have to rethink a lot of the concepts, but that's fine. And for instance, if we use a law of large number, which I think a lot of people will be familiar with these uncertain variables, we find that instead of going towards the mean, as in probability theory, we actually go towards the modes. So we go toward the argmax of the possibility function, and I think that's something that's quite natural, because here there's one value that is true, and basically the argmax is kind of our best bet at what is the true value of that parameter. Similarly, for the variance, if we use the central limit theorem, we'll find that the variance is basically the inverse of the curvature at that mode, and so the pickier the function, the lower the variance, whatever happens for lower possibilities. So that's really something that's local. That's our best guess, and that's how sure we are of that best guess. And those things, they come up naturally. The central limit theorem also actually gives the notion of a Gaussian possibility function, which is very important. I mean, almost everything, when you start with probability distribution, you start in the Gaussian case, and then you work your way from that. So we have that as a possibility function as just as natural. So I'm going to go quite quickly here. Again, the equations are really as pictures. So those possibility functions that are not unique as opposed to probability distribution, and that's good because we can have, I might hold different information from somebody else, and so we all have our own representation of information, but we can still do inference with it. So this is basically saying we can do prediction. This is saying we can do updates. We really can do inference as usual, and in particular here, Bayesian inference. They can be combined, so that you cannot do this with probability distribution, at least not on a continuous space. So, but here, if you're saying, well, I have two objects that I don't know exactly, have some information about them, and then I'm being told that actually those two things, they're equal, then you can really combine that information in a way that's actually basically coherent with our intuition in terms of combining information. So how to interpret this, and this is really important, is that if we think in terms of subjective probability, so we're saying that there's not a true probability, but if we still want to use a notion of probability, we can see the possibility function as giving upper bound and lower bounds on that subjective probability. And that's really important, because if for instance, if f is equal to 1 everywhere, this upper bound is going to be equal to 1, the lower bound is going to be equal to 0, and we're saying that basically the subjective probability could be anything between 0 and 1. Effectively, we'll have no information at all. So how is this relevant for multi-target tracking? So I'm sure a lot of people are familiar with this, so I'll go very quickly here. We assume we have two target trajectories. We observe them. It's not perfect, so we have false negatives. We don't always detect each target. So the observations have some error, and we also have false positives or false alarms, so which make the problem more complicated, of course, because these observations do not correspond to any targets. And so I like this picture just because then I have the version that actually the algorithm receives, right? That's what we actually receive. We just receive sets of observations at every time step. Time is the x-axis here, and that's really all the information is plotted here because it's a very simple 1D scenario. And so it's a lot less obvious here where are the targets and what's going on. So how do we do this? So in addition, actually, I want to add that that was a very simple case. In practice, you also have targets that are appearing and that are disappearing. So you don't know also the number of targets. It might change in time. There are sort of additional complexities there. And so this is really what I was describing with the false negatives, the false positives, and even when we detect, we have some error. So that's a good model that applies to a lot of disciplines, and in particular to SSA. And a very important point here is that we don't know data association. We don't know which observations comes from each target. So one of the usual solution is it's called the PhD filter. And so the very basic idea is that we're going to be interested in how many targets we expect at each point of space. And so this is the recursion for it. I'm not going to go into the details. We're just saying for each point, either there was something where we didn't detect it, or we detected it with one of the observations and with some of our observations. So typically we use those Gaussian distributions. We use the Kalman filter, which is a very important result in probabilistic inference. And so with these observations here, if we apply this, basically we have a function of space that tells us where targets are likely to be. And we see that it does pretty well here. It does pick up the sort of most of the trajectories. This is a very simple filter. I'm not suggesting you should use this for SSA, but I think it's a good example. And in particular, what's interesting is that this result is far from being trivial. It's really thinking in terms of the mean basically value of point processes at different points of space. So it's something that requires a relatively lengthy derivation and introduction of a lot of concepts. But you can do the same with possibility theory. And what's surprising is that you actually get a very similar expression. Here, those symbols are just for maximum. It's kind of the binary version of the maximum. And so, we have pretty much the same expression with a fairly different derivation. And so we can do this with possibility theory. So it's not just solving very simple problems, but we can solve this kind of complex problems, everything using only possibility functions. And in some cases here, I have a scenario where we have a sensor that has a limited field of view and targets that moves around, and the targets also move around. And so, for instance, in this case, actually, we can leverage the advantages of possibility theory to actually get better results. This is the OSPAT distance. So the closest to 0, the closest to the ground truth we are. So, for instance, here actually using a possibilistic approach is in this particular cases is beneficial. What's interesting is that very important results like the Kalman filter actually holds in the same way with possibility theory. So the things that we like and that have been working for very long, those tend to be the same. And then the different aspects, the sort of more complex aspects, then will tend to differ. So coming to SSA, so I'll come back to this picture here. And so basically those lines here, that's what you get if you take the possibilistic approach. And as I said, I think it's a lot more consistent with our intuition that the less we know, basically the more possible is a collision. And basically in the extreme case, we have no information whether a collision will happen or not. And so I think the probabilistic solution here is not quite satisfying, and to some extent neither is the fully possibilistic solution, because there might be some aspects of the problem that are truly random, and if we model them with a possibility function, then we're also missing out. Basically, if the objective is if we use a model that is really faithful, that models things that are well modeled by a probability distribution with a probability distribution, and things that are more deterministic, that are more fixed, but we don't know them, with a possibility function, then we can achieve something that's in the middle. Basically, we're neither too optimistic, neither too pessimistic. And I think that's very important for SSA in particular. We don't want to be maneuvering satellites when it's not necessary. And of course, we want to avoid collision. So there's really this trade-off that must be achieved. And I think we need something that is kind of naturally calibrated and that gives this really this trade-off between the two as naturally as possible. So how can we do this? Actually here I'm going to reference some recent work from Christian Greco and Massimiliano Vasile. I think Massimiliano will talk later. So very interesting work where the idea is that they look at the probability of, let's say, for instance, a collision, and that's so we can define this function phi so that this is a probability of collision given what we observed, and given some parameters that we don't know. And so what they've done is that they kind of minimize or maximize this parameter to find upper bound and lower bounds on the probability of collision, and that is really in the right direction here. Is very interesting, and so they've developed some methodology to do this. So I recommend to check the article. But I think for me that is doing possibility theory. There's really an opportunity to go a little bit further by basically, instead of minimizing and maximizing theta by itself, we can also try to model how likely are different possible values of theta. And so, but we kind of restrain the parameter a little bit further by doing this, and we really learn about theta as well. And that's to do this, we need this notion of outer probability measure. So it's a big term. Outer measures actually are a common notion in measure theory, but here this is an extension of probability distributions where we use both possibility functions and probability distributions. And so once again, we have the subjective probability of collision being in some interval. And here really this is all pictures. I'm not defining all the terms, but we can still bound the subjective probability of collision. And actually, by doing a little bit of algebra, we can find that actually kind of helps to refine the bounds. So have bounds a little bit tighter compared to minimizing, maximizing the expected value. So for the upper bound, I think it's pretty clear that if f theta is not one everywhere, then we're going to have a sort of lower value. But for the lower bound is less trivial, but it still holds where this is consistent with minimization and maximization, but a little bit tighter. But that's not all what I want to do. I think this is the case where we have sort of parameters that we don't know, and then everything else is random. But I think the things could be more complicated than this. So we have initial orbit determination or unknown maneuvers that will be deterministic. But for instance, we might have collisions that might include some random elements, maybe drag, include also random effects. So how to combine all this in a way that's proper and going further with those outer probability measure, that's the question I'm interested in. There are a lot of kind of methodological aspects to this, which I want to look at. This is kind of looking into the future. So I think I already went a little bit over time, so I'll finish very quickly. But and the idea is to put all that into multi-target tracking, and that's feasible. If we can solve for one target, if we can solve the problem, we can put that into multi-target tracking algorithm and really leverage that faithful representation of uncertainty to the best we can. So yeah, take home message, I don't want to do a lengthy conclusion, is really probability theory is not the only thing. We can do something else, and maybe in particular in SSA, that's something that would be natural and indeed useful. Thank you very much.
Thank you very much, Jeremie. That was excellent. And yeah, as someone who would class themselves as mainly in the observational side of research, it's definitely an area that I want to understand a lot better from my point of view. So yeah, certainly with that trade-off, it's very interesting work. And yeah, I think in the interest of sticking to time, we'll move on and let that digest. And if anybody's got any questions, if they enter them into the chat, either directly to Jeremie or I can address them at a later Q&A part of the day, that would be great. But thank you very much again, Jeremie. We'll move on now to our next speaker, who is Laura Pirovano from the University of Auckland. Laura's joining us at very unfavourable hours, so we're very grateful. And yeah, very much looking forward to your talk, Laura. So I'll hand over to you if you're ready to share.
Okay, can you see my presentation?
Yes, that looks okay to me.
Okay, cool. Thank you, James, for the invitation. As James said, my name is Laura. I'm a research fellow at the Te Pūnaha Atea Space Institute in Auckland. I can't raise my voice too much because everybody else is sleeping around here. But what I'm going to talk to you about today is some of the work I've been performing in the past months towards a maneuver detection and reconstruction tool for track-to-track association recovery. A bit of background about what I've done in the past years. My research was tailored mostly on developing tools for accurate description of uncertainty for reliable and fast data association. It was mainly towards the use of optical observations, especially when we had very short arcs where initial orbit determination or orbit determination were not possible. So I tried to extract as much information as possible from a single observation such that then the data association problem could be solved more reliably and faster. However, sometimes, even if we have two well-established states with their own covariance, typical algorithms for data association don't find evidence of association. And that's not because the algorithms don't work, but it's because sometimes we are not observing a debris, we are observing actually something that has moved. So we need to assume that a maneuver has happened in order to recover the evidence of association. And that's why I've steered a bit from the cataloging part towards the maneuver detection, but because this is still part of cataloging, it's very important to keep an accurate catalog. So to develop my tool, what I've been using is convex optimization. So I'd like to give a brief introduction about convex optimization to describe why I chose it and why I think it's the right tool to go. Many engineering problems require solving an optimal control problem. However, there are still some obstacles with direct and indirect methods relating unknowable computational time and lack of assured algorithm convergence. And that's where convex optimization became really, really trendy, because it can solve both problems. It's a class of mathematical programming problems with polynomial complexity, which means it's fast, and it has proven convergent to global minimum. So if it can solve both problems, it looks like the perfect tool. There's still a but, however, of course, otherwise it would be perfect. It can only handle very specific constraints and objective functions. In specific, it can only handle linear objective functions and linear constraints and cone constraints. Well, this would mean that basically almost all our astrodynamics problems wouldn't be able to be solved with convex optimization, being that we work in a highly nonlinear environment, but we can make our problem convex in order to enjoy the beauty of convex optimization and having proven convergence and fast convergence. In order to convexify our problem, there are many things we can do. For example, we can use relaxation, thus turning an equality constraint into a lower than or equal constraint. making it convex, because the optimizer will anyway push the solution to the boundaries, making the constraint equal. We can use an equivalent transformation. Most of the times we will have a nonlinear objective function, which will be the integration of a control law. And we can introduce some slack variables. And since the norm of a vector is actually a convex constraint, we can turn the norm of the control into a convex constraint. And then by discretizing the objective function, we can have a linear objective function. And lastly, we can use successive linearization in case we have nonlinear dynamics. We just perform first order Taylor approximation around a reference trajectory. So all these steps allow us to translate our initial problem into a convex one. But then a question arises. If we transform our original problem into a convex one that has proven convergence and converges to the global minimum, will this minimum be also the solution to our original problem? So what we have to be careful about is that, yes, we are solving a convex problem, but we are not solving the original one. We have to make sure that the solution we found, if applied to the original problem, still holds a good solution. If the solution does not fit in the constraints, then we have to reconvexify our problem around the new optimum, and then iterate until we reach convergence, which is the successive convexification. So in this framework is where I developed my tool, and it's still an ongoing problem, an ongoing algorithm. So both the name and the algorithm are work in progress, and they may change. But the idea was to exploit convex optimization for maneuver estimation, which is the comment. So the approach starts from the fact that we want to reach point A to point B by allowing maneuvers such that the 2 points meet. I firstly propagate my trajectory with high fidelity propagation, because anyway, we want an accurate reference trajectory where we want to apply maneuvers. Otherwise, we risk modeling actually in a model dynamics. So once I have my high fidelity propagation, I just split it into a grid, and I allow a maneuver to happen at any point in the grid. This maneuver would then be propagated linearly forward, and its effect on the state will be propagated forward linearly. So again, I have my reference trajectory, which is very accurate, and then only the effect of a possible maneuver is propagated forward linearly. The final trajectory will then be the actual propagation, the accurate propagation of my initial state, plus the variation that my final state will have depending on the maneuvers that may have happened, plus the variation on the final state due to the uncertainty in the initial state. All these propagated maneuver state will have to meet the final point, because actually that's our goal. And the final point, again, will be a point solution and the uncertainty related to this point. There are many variables involved. There are at least 12 variables for the uncertainty, at least 9 n variables, where n is the number of intervals involved. But this is not a problem with convex optimization, because it can handle a very high number of variables, optimization variables. I'm using Mosaic as a solver, and it can handle hundreds of variables within milliseconds. So that's not our issue. We want to just make sure that the problem is well posed, and all these constraints are linear equalities, which are well handled. Next, what we want to do is to minimize the fuel consumption. We want to find the path with the least amount of fuel used. And as we saw before, we can make an equivalent transformation by adding slack variables at each node of the reference trajectory, and thus having the norm of each delta V, possible delta V at every node. And with these slack variables, we can just make our problem convex. And we can also bound the delta V at each node. The last constraint, but not the least, is how do we deal with the uncertainty in the actual states? Because again, the relaxed Malan-Obis distance is already a convex constraint. But the Malan-Obis distance, so the uncertainty in the states, is not really just a convex bound, because it also holds some statistical data. The further I am from the center point, the further I am from my mean value of the state, the less probable the state is. And we know the optimization always pushes solutions to the limit, which means that if the optimizer, we leave the constraints as they are right now, the optimizer will find the minimum fuel solution, but we'll also push it to the boundaries, making it possibly the least probable solution. So we cannot use these constraints as they are right now. We need to make sure we use them wisely, let's say. So, as I said, this is just a preliminary tool that I've been making. And what I was mostly interested in at the moment was, firstly, that it worked. Secondly, how could I include uncertainty in a good way so that I could actually have some statistical information about the maneuver I'm reconstructing. And third, if there were any coordinate systems that were better than others to describe the problem, or if the problem was coordinate independent. So first of all, what I did, I just simulated the perfect states, and I just created some maneuver so that I could actually test that whatever I did could be reconstructed. And this is an example. I just propagated some TLEs for an amount of time, applied an out-of-plane maneuver, and I tried to reconstruct it with different types of propulsion system, because thanks to the boundaries that we put at every node of the reference trajectory, we can reconstruct the solution with an impulsive or with a low thrust assumption. So by having knowledge also on the propulsion system on board the satellite, which performs the maneuver, we can be more accurate in the reconstruction, in the estimation of the maneuver. Then I found some data from EUMETSAT, from their newsletter, their weekly newsletter. They just released the states of their satellites, their GEO satellites, every 7 days. So I just took them, and I applied them to my algorithm as they were. And of course, if I have so much time to perform a maneuver, and I knew a maneuver had happened, I just didn't know which maneuver happened. If I have so much time to perform a maneuver, possibly the most optimal one, according to the solver, is to perform a little bit of the maneuver at every orbital revolution, which is what the solver reconstructed. However, I knew it only happened once. So by using this knowledge, I restricted the window to just one orbital revolution, just by forward propagating the initial state, backward propagating the second one, finding the moment in which they were the closest, and then limit the search for the maneuver in that orbital revolution. And that's what I did, and it worked quite well. At least I know that I got almost correct the time at which the maneuver happened, because that's the data that EUMETSAT releases. That just doesn't release the magnitude of the maneuver that happens. And the maneuver time does not really coincide with mine, just because mine is a grid, and the grid did not overlap with the actual time of the maneuver. But what the improvement was also in the time, because I did not have to propagate for a week the contribution that every delta V had on the state, but just for a day, and that reduced the time a lot. And what really amazed me at first when I started using convex optimization is the fact that still the solver took 60 milliseconds to perform the optimization. So once I knew that the algorithm was working, at least with the perfect states, it was time to address the elephant in the room. First, I thought I could still include the actual uncertainty in the states in the optimization, and thought I could just create shells around my initial state and see how the solver was optimizing every time while I allowed the state to be more and more uncertain. But again, I wasn't really having much information about the final maneuver, because the solver was still choosing the best point on the sphere where to put the state. So I realized I couldn't keep the uncertainty within the optimization. I had to keep it outside. And that's where I went to the conjugate uncertainty transform, which allowed me to analyze, to perform different optimizations with fixed states. And then thanks to the use of these 4,121 samples due to the 12D nature of my problem, I could reconstruct some statistics about the maneuver afterwards. I was a bit hesitant in using it because of the number of samples I needed and the fact that it wasn't going to be super fast. But what I was mostly interested in was how much information I could extract from the maneuver itself. So this is the same example as before with a EUMETSAT satellite. And we can see here that although possibly the maneuver in the radial and normal directions may stem from some noise, there's clearly statistical evidence that a maneuver in the tangential direction happened, because not only our mean is is above 0, but also the 3 sigma deviation. So it means that for every sample, there was a non-zero delta V in that moment. And we also know that a maneuver happened because that's the data we have from EUMETSAT. So I was quite pleased with the result. And all in all, it did not take that much. It took around 27 seconds. That's not great, as in overall, if we want to apply it to the entire catalog, but it only took around 5 seconds to create the reference trajectory with all the possible, with all the variations, and then parallel computing allowed to analyze all the 4,000 Ks in only 20 seconds. So all this was performed with Cartesian coordinates, because I only analyzed LEO and GEO orbits, and they were circular. Cartesian coordinates work quite well. I already had my dynamics written in Cartesian coordinates. It was easy to include maneuvers, so I just went with it. However, I knew that having all components of the state varying so much during the orbital period, the assumption of linearity might not hold. And indeed that happened when I tried with eccentric orbits. I just got my optimal delta V profile, which looked okay, but then when I had a look at the semi-major axis, that's when I realized something was wrong. And when I included the optimal delta V profile in my original problem, I knew I was clearly nowhere close to where I wanted to be. And I had to remake the problem convex, so perform successive convexification to actually reach the point where I wanted to be on a second loop. This is, of course, doable, but since it's already taking quite a bit of time, doing everything twice, it's not really what I wanted to do. So I went on and tried different coordinate systems to see if the same pattern happened, or the coordinate system actually had some influence on the final result of the convex optimization. So I tried orbital parameters, because they only have one fast variables and they don't really have a cone. I just made some transformations among different reference frames. And they actually did converge within one iteration, also for eccentric orbits. So to answer my question, yes, the choice of the reference frame does make an impact on the convex optimization. And so I guess this is the way to go forward and depend on the Cartesian coordinates. So in conclusion, I started using convex optimization, and I do believe it's a powerful tool. And with the right coordinate systems, it's possible to obtain convergence in all regimes with one iteration. And thanks to the use of the conjugate uncentered transform, it's possible to obtain statistics on the maneuver. But it's really important to still be careful, because what we are solving is not the actual real initial problem, it's a convex problem, and we need to make sure that it's also solving our original problem. Next up, I want to, of course, try different coordinate systems, since I realized that they do make an impact on the final solution. And I also want to try and exploit more the knowledge on possible maneuvers, and maybe use primary vector theory to create an intelligent grid, because there will be places where it's most probable that the maneuver has happened. So I want to place my grid exactly in that place. And of course, then I need to test more, have more data, and then make sure that my algorithm is robust in all the different regimes. And then it always, it works, let's say. So I thank you very much, and I hope I didn't bore you too much.
Not at all, Laura. That was very interesting. Thank you. And yeah, again, thank you for joining us so late. It's much appreciated. Are there any questions for Laura or Jeremie beforehand in the chat? I don't see anything in the chat, but if you have one now, please raise your hand. I've got a couple of questions, but I think for the benefit of time, I'll follow up with you at a later time, Laura, because we can have a proper discussion.
Sure.
But yeah, not seeing anything coming through. So thank you very much again, Laura. And we'll move on to our next speaker now. So that will be Dimitri Veras. And Dimitri is another member of our Centre for Space Domain Awareness at Warwick. And he'll be talking to us about the Yarkovsky and Yorp effects in planetary science with potential SSA applications. So thanks very much for joining us, Dimitri, and I'll hand over to you.
Okay, thanks a lot, James, for that introduction. Hi, everyone. Today, I'm going to discuss two physical effects, the Yarkovsky effect and the Yorp effect, and I'm going to describe how they actually influence space debris. So first of all, let me define these two effects. So the Yarkovsky and the Yorp effects are the result of radiative forces due to photons from the sun impinging on an object. And that object can be any piece of space debris of any shape. Now, although some of this incoming radiation is immediately reflected, some of it is instead absorbed and internally redistributed within the object. So some of this internally redistributed energy, it can be reflected in the same direction after some delay, and some can be reflected in a different direction after a delay. And as a result, the object's spin angular momentum and its orbital angular momentum can both be changed. So the torque that's actually produced from the spin angular momentum is known as the Yorp effect, and that causes the object to spin up or spin down. Also, the force imbalance that's actually produced from the orbital angular momentum change, that is the Yarkovsky effect, and that changes the orbit of the object. And if you're wondering just how much of an extra acceleration photons can actually produce on an object, the answer is on the order of a picometer per second squared. Now that sounds tiny, and it is tiny, but yet that small acceleration has generated great interest in some communities. So here, what you see here is my rough summary of the research fields for which the Yarkovsky and Yorp effects have been investigated. Now, as you see on the bottom, for SSA, it's about 10 papers in total. Also, as you can see in the middle, for extrasolar planets, it's also about 10 papers. However, for solar system science, with about 200 papers, I mean, practically a mini industry has sprung up around these effects. And therefore, when we apply these effects to SSA problems, we should first learn the lessons from the large body of literature which has already been published about the solar system objects. However, we have to appreciate the different contexts in which the Yarkovsky and Yorp effects are actually applied. And that's summarized on the right of the slide. Is when talking about asteroids that are orbiting the sun, or any stars, we are thinking on million to billion year timescales. Whereas instead, for SSA, we have to decrease that timescale by 5 to 8 orders of magnitude. I mean, a gigantic difference, literally. Also, it's important to consider that space debris, which we care about the most, orbits the Earth and not the sun. And that difference has implications, because analytically, one has to then reformulate the equations and also introduce shadowing, for example, when Earth is blocking the sun. Also, potentially, one might need to consider how to incorporate reflected light from the Earth in the Yarkovsky and Yorp effects. And also, as for the sizes of the objects, we are considering the lower end, with sizes corresponding to artificial satellites and various pieces of debris. So I wrote here 10 meters as the SSA upper limit, and we could go higher depending on how big of a satellite that you are considering. But with SSA, we're not looking at asteroids, and certainly nothing above 1 kilometer. So then what about the lower end? And I've used 1 centimeter here, and now I want to show you why. So this plot illustrates the minimum diameter of an object at which the Yarkovsky effect turns on, based on arguments about the penetration depth of the radiation. Now, this critical diameter is equal to the penetration depth scaling D, which is in the legend on the right. And this value D is a function of the object's thermal conductivity K, it's on the y-axis, and the thermal capacity C on the x-axis. Now, the object here was assumed to represent a high density piece of debris, something iron-based with a density of 8 grams per cubic centimeter. Also, this little piece of debris is assumed to be spinning with a spin period of about 3.5 hours. And so given these assumptions, this plot illustrates that for just about any thermal conductivity and any thermal capacity that you choose, the smallest object diameter at which radiation can penetrate to create the Yarkovsky or Yorp effects is on the scale of about 1 centimeter. So far, so everything I've told you up to now might sound pretty theoretical, but now I'm going to show you some plots which demonstrate just how real these effects actually are. And this plot shows spin periods of asteroids versus their diameters. And so the slowly spinning asteroids are towards the bottom and the quickly spinning ones are towards the top. And all the data points here are real. Nothing is simulated. And what you can see is a fairly stunning cutoff for objects larger than 1 kilometer at a vertical value, which corresponds to about 2.3 hours. Now, in the legend, the authors refer to this as the spin barrier. And something in nature is preventing asteroids from having spin periods shorter than 2.3 hours. And that something is the Yorp effect. It's over millions and billions of years, the Yorp effect has been spinning these asteroids up to break up speed and then literally breaking them apart. And most asteroids larger than 1 kilometer are rubble piles, and these rubble piles break apart at a spin period of about 2.3 hours. So can the same thing happen to space debris? Well, that's doubtful because look at the left-hand side of this plot. Pebble and boulder-sized objects are not so easily broken apart given their internal strength. And each of those green diagonal lines corresponds to a different internal strength. But what Yorp can certainly do is change the spin period of the space debris and affect their light curves, even if Yorp can't break them up. So the Yorp effect is real. How about the Yarkovsky effect? Well, this plot helps to show that the Yarkovsky effect is real too. This plot shows semi-major axis drift, measured semi-major axis drift, over decades of observations as a function of diameter. Now that red diagonal best fit line, that shows a correlation and a nearly inverse correlation with diameter. And that is the correlation we actually expect, at least roughly, with the Yarkovsky effect. So both the Yorp and Yarkovsky effects are real. And now the question is, how do they affect space debris? So let's start with the Yarkovsky effect. So this plot shows the relative accelerations of the Yarkovsky effect versus the accelerations generated from the oblateness of the Earth as measured by J2, J3, J4, J5, and J6, and also the acceleration from solar radiation pressure, solar gravity, the moon's gravity, and Jupiter's gravity. And as you can see, the Yarkovsky effect is on the bottom. It's the weakest of all of these forces. Even the acceleration due to Jupiter is greater. And note here, the x-axis is for geo objects, but even moving to Leo, the situation would not change much. So how does such a small acceleration translate into displacement over observable timescales? Well, the answer is partly revealed by this plot. So this plot shows the time evolution of the orbit of space debris affected by solar gravity, and that's in the black curve. And then the other curves include the sun's gravity plus the Yarkovsky effect. So the other curves, those are distinguished by different rotation periods of the debris, as you can see in the legend. Now remember that the Yarkovsky effect creates drift, not a change in rotation. Nevertheless, the spin state of the debris does affect that drift. So in terms of initial conditions, the debris modeled here begins at a semi-major axis of 42,164.0 kilometers on a nearly circular and coplanar orbit. And note that the x-axis spans about 200 years. So the takeaway from this plot is that over the course of, say, 50 years, the Yarkovsky drift does not exceed a kilometer. Now, is that important? Well, that depends on your SSA application. But remember that if you did want to model debris at this level of precision, you would need to include all the other effects too. So overall, the Yarkovsky effect can often be ignored, but the story for the Yorp effect seems quite different, because the acceleration generated by the Yarkovsky effect is overwhelmed by these other effects, but the Yorp torque has almost no competition. And in that sense, any deviation from the object's predicted spin state should be due to the Yorp effect. Now that's quite a powerful statement, not an entirely correct one, because if the debris is actually large enough to have some type of internal decaying energy source, or even something more mechanical like remaining fuel sloshing about, then that source could actually change the spin just as well as Yorp can. But because of the perceived greater importance of Yorp than Yarkovsky in SSA applications, nearly all of the SSA-related papers tend to focus on the Yorp effect. So I'm going to describe one of those now, or discuss one really in a bit more detail. So the Yorp effect has been modeled somewhat extensively on the GOES satellite. There's a series of satellites, actually. And these satellites were geostationary NOAA weather satellites. They were launched between 1994 and 2001, and they were retired at different times between 2004 and 2013. Now, the asymmetries of these satellites, which you see here, they actually should provide an important test bed for Yorp effects. And also, the end-of-life mass properties for these satellites are actually well documented. And so obtaining light curves and radar observations is relatively easy, all of which make these satellites great targets to study. And for this reason, GOES satellite number 8 was actually a focus of multiple papers. And its end-of-life evolution has been interesting. In December 2013, the rotation period of GOES 8 was about 16.8 seconds, as you can see here. And that value deviated by only a few tenths of a second in the subsequent 2 months. However, just 2 months later, that spin period increased to 23 seconds. And then 3 months after that, the spin period was 75.7 seconds. And finally, 18 months later, the spin period jumped significantly to about 12 minutes. So the interpretation for this increase in spin period was that the satellite moved from a state of steady rotation to one that is tumbling. And this notion was reinforced by the light curves. So here you see the light curves for 3 of the epochs. In the upper left is the first epoch with a spin period of 17 seconds. In the upper right is the light curve for the satellite when it had a spin period of 76 seconds. And by comparing the two, you might be able to eyeball the difference in periods. Also note, of course, the number of magnitudes in which the light curves can vary, which is quite significant. Now, the lower plot was the last observation taken 3 years after the first observations. So here, the spin period had jumped to 12 minutes. And when I say 12 minutes, I'm just giving an approximation. Actually, the apparent period is changing rapidly. And that characteristic is consistent with a tumbling state. So those are the observations. And the next question is, can the Yorp effect model this transition from steady rotation to tumbling? So the answer is yes. And what you see here is the evolution of 3 components of the angular velocity based on the Yorp model that these authors have implemented and ran. So the initial conditions for the simulations were those on December 2013, and the simulations were run for 1 year. And then after about 260 days, the satellite indeed enters into a tumbling state, which I've indicated here by the highlighted area. And so how do these changes actually translate into simulated orbital periods? Well, this plot shows a direct comparison between the simulations and the observations with regard to spin period as a function of time. And so a plot like this one illustrates 2 important points. The first one is that the Yorp effect does have a measurable influence in SSA contexts. And the next point is that simulations can succeed at reproducing observations by actually modeling the Yorp effect. Now, as for that modeling, there are important computational choices to make. So these authors, they actually modeled Yorp in 3 different ways. And the first way, which is the slowest, but the most accurate, involves no averaging at all, actually. And the result is the blue curves on these plots, which shows the most accurate evolution of the Z direction of the angular velocity. Now, the next way, which is quicker, is when the equations are averaged over the satellite's rotational period. And these curves are given in green and demonstrate that this method mimics the true evolution, but with an error on the order of days to tens of days. Now, the fastest method is to perform a double averaging, which is once over the spin period and then once again over an orbital period around the sun. And these curves are given by the diagonal red curves. So what those curves successfully do is demonstrate the yearly trend of angular velocity variation without providing any additional detail. And this trend is what would be known as the secular trend. So these plots, they demonstrate that having available different Yorp models may be important depending on the problem that you're trying to solve and the timescales that you are looking at. So on the bottom of the slide, I've listed 3 more papers where the authors have all developed Yorp SSA models and have also applied them to the GOES satellites. Now, these papers all come from Dan Shear's group from Boulder, Colorado. Dan is a pioneer in this field, and he's written several important Yorp papers in the field of solar system science. And by the way, the first author on those papers, Connor Benson, he actually attended the same virtual conference that I did last year, the Division of Dynamical Astronomy Conference. And I asked him about what he thought the most next important physical effects are to model for the GOES satellites. And he said he thinks it's internal energy dissipation. Note also that the 4 papers on the slide, they're from different journals. One is Advances in Space Research, another is Acta Astronautica, the third is Journal of the Astronautical Sciences, and the fourth is the Journal of Guidance, Control, and Dynamics. And especially if you're relatively new to this field, that gives you some idea of the breadth of journals where it's important to keep track of. So in summary, there's several points that I'd like you to take away from this presentation. And the first one is that depending on your application, the Yorp and the Yarkovsky, both the Yorp and the Yarkovsky effects could be important. The Yorp is more likely to be important because the Yarkovsky effects only provide a drift of about 1 kilometer or so over 50 years, whereas Yorp doesn't really have any competing effects. And so far, the Yorp effect has only been studied for a handful of satellites. So potentially, there's a lot more to do in this area in terms of applications. In terms of models, there are already models in place. And in terms of how much those they can be improved, that's another outstanding question. But I really get the sense that there are more applications that need to be done. So thanks for your attention, and I'll be happy to take questions.
Thank you very much, Dimitri. And yeah, great to see the crossover between disciplines there. Are there any questions for Dimitri? I don't see any hands. I know there were a couple of comments that came through via the chat, but I don't think there are any questions as such. So maybe, Dimitri, if you can go back and address those if you'd like to. But yeah, I think that brings us nicely to the time for the next speaker. So thank you very much again. And I'll introduce our next speaker, who is Camilla Colombo from the Politecnico di Milano. And she'll be talking to us about space debris fragmentation reconstruction with the puzzle suite. Camilla, do we have you there? I think you're muted at the moment.
Yes.
Brilliant.
Yes.
Thank you very much. You should have permission to share your screen or slide, so please do so when you're ready, and otherwise I'll hand over to you. Thank you.
Thank you. I'm now sharing the screen.
Yeah, that looks good to me.
Okay. So good afternoon, everybody. Thank you for organizing this this Sandpit. Today I will present you some work we have performed at Politecnico di Milano for reconstruction of space debris fragmentation on the short term and the long term after a fragmentation event. The background starts from the increasing number of object launch every year, and therefore also the increasing number of fragmentation, deliberate or not deliberate fragmentation. There are several approaches for detecting fragmentation, and we can divide them, for example, on the short term and the long term after the fragmentation event. And in general, the important aspect is to define some metrics to find similarities between the different fragments belonging to the same fragmentation, and then to perform some analysis to link them to their parent object. And this is what we try to do in the puzzle suite that was developed thanks to one project funded from the Italian Space Agency in support to the EU SST services, and for the long-term evolution through the ERC project Compass. The goal of this suite is to perform the detection of recent fragmentation. More than detection, we mean the reconstruction of those fragmentation, because we start with the TLE observation of fragments as input of the tool, and then to characterize their mass and their energy, and to link them to the possible target, the possible parents satellite. So we perform a sort of reverse engineering of the fragmentation thanks to backward propagation and analysis of the orbital mechanics. And this is done with a series of filters, and as I said, with backward propagation, and I will present step by step all the approaches. So the tool as an input takes as input the TLE of a non-catalog object that comes from observation. In the recent anti-satellite test in November, we were provided some TLE coming from different sensors in Europe. It takes as input a search parameter, for example, the time interval or the distance margin within which we want to find a possible fragmentation, and add other additional parameters. And then it gives as an output the probable event epoch and the possibly involved object, the distribution of the fragments, and the characteristics of that fragmentation as reconstructed through the models. And in particular, as I said, we can consider two possible scenarios: a scenario of a fragmentation that happened long time ago, and therefore we use long-term analysis, and instead short-term analysis for fragmentation that happened within days or weeks from the time in which the analysis is performed. Let's start with the short-term analysis. And let's describe each one of the blocks. So first of all, we start with reading and pre-filtering the initial data. So imagine of having an initial set of TLEs. Some of them, hopefully, they are part of the fragmentation. Some other are uncatalogued objects that are not part of that fragmentation event. To this initial set of TLEs, we apply a series of filters in order to remove outlier and remove objects which are not part of that fragmentation. A filter on time, a filter on the mean motion, a filter on the inclination and the eccentricity, and a filter on negative B star values or values which are might be associated to maneuvers. Then we move to the next step, that is about pruning and clustering, and this is performed through a set of filters, a 3-loop filter. First of all, an apogee and perigee filter that checks that the fragments can have correspond to some criterion in order to have a possible intersection among them, where this intersection means that they were part of the same initial orbit. Second, a MOID filter. So we filter the geometrical minimum orbit interception distance between the different orbit of the different fragments. And finally, a time filter that works with some angular windows, checking that the fragment are passed through a certain position in space. The next step is to perform some backward propagation, and in particular for the short-term analysis we use SGP4 as a propagator, while for long-term analysis we need to change the orbit propagator. And this allows determining the time around which the fragmentation took place. And then the next step is the identification of the target by using some similarity distance metrics, which are similar to the one used in asteroid studies for dividing asteroid families into asteroid families. And so in this way, we cluster different fragments with respect to their orbital elements, for example, the right ascension of the ascending node and the inclination. And the last step, once we have identified the fragment belonging to the fragmentation, we can now try to reconstruct the fragmentation. So now going forward, using a fragmentation model, for example, in the implementation of the puzzle tool, we use the NASA standard breakup model. In this way, we can provide an estimation of the characteristic length, the characteristic length of the fragments and their distribution in terms of velocities and area to mass ratio. As an example, we have applied this tool to a very well-known fragmentation, the collision, the Iridium Cosmos collision, considering the event epoch and taking the TLEs generated 7 days after, the TLEs available 7 days after the event. In this way, we can use this test case to search for the breakup event, identify the epoch of the fragmentation, identify the families of objects involved in the event, and finally performing some analysis like the Gabbard diagram, fragmentation modeling, and so on. So in terms of result, we have started with a set of around 2,000 TLEs, some belonging to the fragmentation and some not, taken, as I said, 7 days after the event. And in this figure, I will show step by step what the different blocks of the diagram do. So we have a pre-filtering, then searches for orbital intersection, and then the identification of the epoch in terms of time of the fragment of the collision, which is found with a margin of 1 minute. And in that way, it's possible to identify the 2 orbital families in the estimated interval. In this case, we have identified the 19 objects belonging to that fragmentation. And so we can reproduce the Gabbard diagram associated to the 2 families of objects at the epoch of the event. And all of this requires a computational time of around 10 minutes. At that point, we can use the NASA breakup model to model the fragmentation itself. In particular, we need to set the parameters of the masses if the mass is involved, the number of fragments, and so on. And we can characterize the distribution of the physical properties of the fragment. This post-analysis is performed because we are currently working in also reverse engineering this part. So once the fragment are coupled with the two parent objects, we want to go back to the initial condition that created this collision or this fragmentation in space. So to be able to reproduce the complete Gabbar diagram at the epoch of the event, because if we compare this Gabbar diagram now as more fragments, because some of them are simulated through the breakup model. And then instead of moving on the long-term analysis, I will now describe what changes when we want instead to extend the reverse engineering model to a long-term analysis to understand and to study fragmentation that happens in the order of month or year before the time of analysis. More or less the code block diagram of the approach is similar, but with some differences. In particular, we need to perform the ballistic coefficient parameter estimation. This is done by using the average variation of the orbital elements and comparing the change in semi-major axis that can be calculated from the two-line element with the semi-analytical change of semi-major axis that can be calculated through semi-analytical equation considering drag or also adding the effect of solar radiation pressure. And this cycle is repeated until we can have a match between the delta, the variation of semi-major axis from real observation, so the TLE, matching the delta semi-major axis of the propagated tool. And this is done following an approach by Gondela and Armelin. Then we still perform the triple loop filter as before with an additional inclination filter, which is added only for long-term analysis. This has no much effect in low Earth orbit, but is important for clustering the fragments in terms of inclination ranges. So as before, we can start with the large set of fragments to identify only the fragments that are whose orbit have a point in common. Another difference is the propagation. While before in the short-term analysis, the backward propagation was performed with the SGP4, considering J2, gravity harmonics, drag, solar radiation pressure, and lunisolar perturbation. On the long-term analysis, mainly to speed the computational cost, we use semi-analytical techniques. So we just follow the mean variation of the orbital elements with a semi-analytical tool, Planodin, that we have developed at Politecnico di Milano. And then we move also to, let's move to a validation case for the long-term analysis. This was performed on the fragmentation of Fengyun 1C, and it was considered an initial condition 10 months after the event. So with respect to before, we are looking at the fragmentation that happened much more in the past. Again, we provide to the tool some fragments belonging to the fragmentation and some other not cataloged fragment. And also in this case, we can estimate the epoch of the fragmentation and the relative error, and we plot here the relative error with respect to the real point of the fragmentation. Some consideration is that depending on the fragmentation, many parameters affect the results and in particular the accuracy of the analysis. So it's important to, let's say, it's very difficult to automatize the search because the threshold for all the, for example, the threshold for all the filters and the pruning depend, first of all, on the fragmentation case, but even more especially on the uncertainties associated with the observation that are then creating the TLE elements that we consider as input. Of course, the computational cost depends on the number of TLE that are examined. Therefore, it's very important to work on pre-pruning and pre-filtering of the initial condition in order to remove the outlier in this analysis. In both cases, we have seen some good accuracy, both in short and long-term estimation, in the capabilities of detecting the breakup event, estimating the epoch or the window for the breakup, in identifying the object or the objects involved in the fragmentation, and in identifying the parents on the short term or the candidate parents on the long term. As a future and current work, we are now working on the improvement on the identification on the event epoch and object identification, improving the ballistic coefficient estimator, the P-star estimation, and a lot of effort is put now in the automation of this approach, because as I said, it's very important to properly set the threshold in terms of pruning and filtering. And finally, we are working to include the uncertainties in the measurement, because now the TLE are taken as an input, but we are not considering any uncertainty in those measurements. And we are aiming and looking at validation with observation data, and therefore we are open to collaborate with anyone that has some observation data available. With this, I thank you for your attention, and I also thank the co-author of this work, because I forgot to do it at the beginning, Andrea Muchacha and Matteo Romano.
Thank you very much, Camilla. That was excellent. And yeah, very, very interesting area of research. I had a brief question. If anybody else has a question, please raise your hand or enter it into the chat. So mine was sort of focused around the long-term evolution, and do you have a sense yet of just how old a fragmentation can be and still be, it still be plausible to be able to assign elements to that particular fragmentation? So I know there's a lot of fragments in, say, the high altitude regions that are still unidentified and not assigned to a launch or an object. Is there any hope of doing that in the future?
Yeah, thank you for your question. Actually, we have developed this long-term analysis for two reasons. The first is, as you say, to develop the capability of maybe identifying or characterizing, more than identifying, some fragmentation that happen on the long term, and we are talking about months or years after the fragmentation, few years, or let's say around 1 year after the fragmentation. And this is relevant maybe for fragmentation not in LEO, but in medium Earth orbit or GEO or highly elliptical orbit, so region which are a bit less observed than LEO. And the second reason, which maybe is the more important, is that after a certain time before the fragmentation, SGP4 is not anymore the good propagator to actually perform the back propagation, but we haven't yet defined the threshold of time when to pass from a SGP4 to a higher fidelity propagator. So the idea of analyzing also the long-term analysis is then, depending on the orbital region, in defining a threshold when to pass from one propagator to the other one. And this threshold depends on the altitude of the orbit and depends on the accuracy of the observation. So it's something that we are working on because it requires a lot of work and analysis.
Thank you. Yeah, that clears things up. I don't see any other hands up or anything else in the chat. So I'll thank you again, Camilla, and thank you very much for joining us. There'll be a discussion period in about 20 minutes time. So if you're able to stick around for that, hopefully things will digest and some questions may arise then. But yes, thank you very much again. We'll move on now to our next speaker, who is Paul Chote from the University of Warwick. And he'll be talking to us about observational recovery of electric propulsion orbits. So Paul, if you're ready to share, I'll hand over to you.
Yep, thanks, James. Right, is that visible?
Yep, looks good to me.
Okay, right. Thanks, James, and hi, everyone. Yeah, so today I'm going to talk about, first off, a small project that we did in the context of understanding and observing the Mission Extension Vehicle 2 and its orbit raising, proximity operations, and subsequent docking with Intelsat 1002. So there's a little bit of an introduction. The mission extension vehicles, the idea is that they're servicing satellites that can extend the lifetime of clients by flying up, basically attaching to them using this docking system that clamps onto the liquid apogee motor on the back, and then takes over their propulsion and station keeping duties for the lifetime of their kind of contract. And then at the end of that, they can fly, raise the orbit up into the geo graveyard, drop off the client, and then go and service another spacecraft. So for the context for this talk, the thing that's interesting is that MEV2 uses electric propulsion. So very low thrust, so very slow orbit raising. So MEV2 launched in August 2020 and spent about 6 months getting up to GEO. And so this was in the context, falls under the umbrella of Phantom Echo's project, which was a Five Eyes collaboration. And a lot of this work was subsequently written up and published in an AMOS paper. And I see some of the names here are also in the audience today. So yeah, more information, you can have a look at this and we'll be happy to talk about it more later. This was a fairly large undertaking with observations taken from many telescopes around the world. My focus in this and the next couple of talks is on our facilities based on the island of La Palma in the Canary Islands. So we actually have 3 talks related to this. This is the first in the middle, where we used University of Warwick's SuperWAS facility, which is down here, if you can see my cursor. And then after the break, I'm going to have another somewhat longer talk about high-speed photometry and color photometry and how that relates to what we can understand about the properties and characteristics of geosatellites. And then after that, we'll have Klaas talking about some work on doing polarimetry of the satellites. But back to the topic at hand. So you've got this electric orbit raising. MEV2 was first launched into a highly elliptical orbit, quite a low perigee, apogee up near GEO, and then spends several months circularizing and raising its orbit. And so you see the different orbital parameters change quite smoothly, mostly, but have lots of kinks and wiggles over time. And what this means is that the TLEs are not a very good description for anything but the time of the observation. So we can try and quantify that a little bit more directly. And so what these plots are showing is the separation on the sky. So you evaluate the previous TLE at the time of the next TLE, and then just measure how different the positions are on the sky. And so at the time of epoch, we can see most of the TLE updates are within a day, but there are quite a few instances where you get 2, 3, 4, up to a week without getting fresh TLEs. And in that time, we can see that the separation, so where you'd expect to find it, is actually as much as 20 degrees or more. But that is at the time where it was picked up. So by definition, someone was able to observe it and give that data. Whereas for kind of arbitrary observations, what you actually care about is the maximum separation within an orbit, which includes the lower altitudes where it's moving faster and has larger separations on the sky. And you can see in this situation, there is actually quite a significant fraction of the time, the TLE predictions are more than 10 degrees away from where it actually is. And so there's one strategy, taking it from a kind of TLE perspective, that you can improve on this. Because you know that most of these parameters are varying relatively smoothly, you can actually interpolate, or when predicting ahead, extrapolate a synthetic TLE that gets you hopefully a bit closer to where it is. And this works pretty well when you have good constraints. So in this example, where we're kind of looking back retrospectively over a relatively nice linear region, we can get quite a good recovery. So we've got these two images on the right of the slide. The top one is when it's at a relatively lower altitude and a relatively smaller range from our telescope. So the projected separations on the sky are much larger. So the TLE prediction is 12 degrees away, but when we reconstruct the synthetic interpolated TLE, we can get it to within half a degree or so. And then even at the higher altitudes, a couple of hours later in the orbit, where all of the predicted separations collapse down to a much smaller separation, the TLE is still a good 4 degrees off target. Whereas once again, recovering from the interpolated TLE is within half a degree. So the red lines here are the interpolated predicted streak locations, whereas we can see here streak and much smaller streak down here. So to put this into context, we need to think about, well, TLEs don't come from nowhere. Someone has to actually get a sensor on them. And these sensors have finite sizes. So I've just got a little bit on kind of telescope fields of view. So in this kind of top left corner, we have typical fields of view for astronomical research telescopes. So big aperture, fancy instrumentation, but typically very small fields of view. In the middle, I have a kind of research telescope designed with a wide field camera system, which gives you a field usually comparable to the size of the moon. Whereas on the bottom, I've got examples of two types of astrograph, which are specifically designed for kind of wide field imaging. And a lot of the telescopes used for SSA purposes are of this class. But even then, you can see if your field of view is only of order 3 degrees, it's going to be very difficult to find your object when the TLE prediction has an error of 10 degrees to 30 degrees, say. Yeah, so you kind of, if you're dealing with telescopes with this kind of field of view, you have to start playing tricks with your data and with your predictions to be able to actually find the thing that you're interested in. So the other perspective is to say, well, what happens if we just go to even larger fields of view? So we have our SuperWASP instrument, which is a much larger field of view, 15 degrees aside. So to scale compared with the other images here. Once you get to these ultra wide field of view, it actually becomes quite simple just to tile the whole sky. And within a few minutes, you can survey several thousand square degrees and just measure the positions of everything along the track. The issue then becomes saying, well, we have observations with 150 or 200 detections that are consistent with, with satellites, and maybe 1,000 or so false positives. How do we actually recover the thing that we're interested in this case, MEV2 in its elliptical orbit? So what we can do is we can construct a useful coordinate system, which is basically the tangent plane of the observation co-moving with the TLE position. So what this does is it moves with the TLE, and it accounts for the scaling that happens when the range is small, everything appears larger on the sky, whereas when the range is further away, everything's smaller. So we can back out to first order those effects, and you end up with a two-dimensional map with basically physical distance offsets. And what we see is that most of, you have a background of randomly distributed false positive detections, but then we find that the object that we infer to be MEV2 always lies on the zero cross track and some distance along track, either behind or very occasionally in front of the predicted TLE position. And in this case, that could be kind of 3 degrees behind, or as much as 20 degrees or 30 degrees behind. And you get all of the other satellites in the field of view. Because the orbit in this case is elliptical, the track across the sky is very different to everything else. And so by adopting this coordinate system that co-moves with the original TLE, even though the orbital parameters have changed, that mainly accumulates into the phase of the orbit. Things like the inclination are much slower to change. So the main offset that we expect is along this vertical direction, whereas all the other points cluster together. And so we can just look for where the most clustered collection of points are, and then from that back out all of the detections for the object. And this is an extremely computationally efficient technique. It's milliseconds. You don't have to do any correlations. You don't even have to have knowledge of the other satellite TLEs. All you need is your single last known TLE. And then the data itself tells you the object that's most likely to be, in this case, MEV2. So we then applied this a bunch of times. We had a few failures at the start, which was mainly due to problems with scheduling that we were able to solve, and showed that this method consistently works. So we were able to quite reliably recover MEV2 when it had offsets of as much as 30 degrees away from the TLE. So TLE ages of kind of two days old, when it would have been completely hopeless to try and find that with a standard sized field of view telescope. And yeah, so that's all I want to say about this part of the project, but I will be back after the break with the next talk. So thank you very much.
Thank you very much, Paul. And yeah, certainly a lot to digest. I think there's probably a lot of crossover with some of Laura's work on maneuver detection there to exploit at some point. Yeah, so I'll just, if you're happy to stop sharing your screen, I'll get the schedule back up and we'll go into the discussion part of the day. Just bear with me. Okay, is that visible?
Yes.
Brilliant. So yes, moving into some discussion now. So this is an opportunity to essentially ask any questions that you may have for any of the speakers thus far, and also just raise any particular discussion points that you may want to address. I've probably got, as I said, a couple of questions for Laura, but I think they're a bit too in depth to go into right now. So if anybody has anything, if you raise your hand, or we can go into our break early. We got something in the chat. What was this? Oh, that was just Laura. Okay. Not seeing anything coming through. So what I might say is that we go into our break slightly early and take advantage of that fact, and then we can head into the second half, which is quite a packed schedule, with a few minutes gained. So if I move forward to the second half, you can see that here. If we say we'll meet back here by 3:10 instead, so that gives us a decent sized break ready for the afternoon, but also starts 5 minutes earlier than planned. So if that's if the future speakers are happy with that, otherwise feel free to object now. But yeah, just to also point out, we've got our details in the bottom right-hand corner here. So feel free in the meantime to check out our website for those funding opportunities that we mentioned throughout and at the start. We've also got our Twitter handle there if you wish to follow us for regular updates of events and deadlines and such like. Yes, please feel free to check those out. But yeah, we'll return here in, what was it, 25 minutes time, so 3:10. I'll adjust this time so it's on show, and we'll resume our schedule thereafter. Thanks very much, everyone, and thank you to our speakers so far. Okay, welcome back, everybody. I'll just go through a few logistical notes again while people are connecting back up, just in case we've got anyone joining us new from this morning. So yes, if you do have any questions for our speakers going into the latter half of this event, please do raise your hand as we go, and I'll look to invite you to the floor as we go along at the end of the talks. And also, please do keep yourself muted when not speaking, just so that we don't have any distractions for our speakers. But yes, moving into the latter half, you can see we've got quite a packed schedule, but if all goes well, we should be finishing just after 6 p.m. GMT, depending on discussion times and so on. So I'll introduce our next speaker, which is again Paul Chote. He'll be moving on to discuss the main observation campaign that was performed to monitor the MEV2 rendezvous and proximity operation. So Paul, I'll stop sharing and hand the floor to you again.
Thanks, James. Right, is this visible and can you see the cursor this time?
Yes, I can. It's a little red dot, yeah. Okay,
perfect. Right, so continuing on from my last talk, I'm now going to talk about our high-speed light curves and color photometry efforts on MEV2 and Intelsat and the surrounding nearby satellites. So this observation campaign started at the end of January, which was when MEV2 finally reached the 1 degree west orbital slot where Intelsat 1002 is. And it was originally planned just to take a couple of weeks over what was then assumed to be the docking date. But actually, for various reasons, the rendezvous and proximity phase of that mission was extended by several weeks. And so our observation campaign had to stretch to match. And in the end, we ended up getting around 45 nights of data spanning about 3 months with our small telescope and a scientific CMOS camera. Which we augmented with another 25 sets of color observations using the GoTo prototype telescope, which I'll come on to a little bit later. And so this is what our data looks like, and there's a lot to unpack here. So I'll spend a little bit of time going into this. So in this panel at the top is a subsection of one of the frames, one of the raw images from the telescope. And from that, we see 6 individual blobs, which are satellites, geostationary satellites. And these streaks are the background stars. So the telescope is staring at a fixed patch of sky, and the stars are moving behind it. Because each of these exposures was 5 seconds long, the stars are elongated. And we can use these elongated star streaks to very accurately calibrate both the absolute pointing of the telescope, and from that measure very accurate positions for each of the satellites. But also we can calibrate the brightness and get very accurate absolute photometry for the objects in the field. And so these brightness measurements for each of the satellites, which are color-coded as shown, are in the panel below. And so what we have here is the satellites are reflecting sunlight, and we have something known as the phase angle, which represents it's kind of like time, but it also folds into account the fact that different positions on the sky have a different angle relative to the sun. And so the idea is that a 0 degree phase angle would be where the satellite is directly opposite the sun. And in larger phase angles, you have the sunlight being reflected off at larger and larger angles. And so as the Earth rotates, the satellites are geostationary, so the satellites are also rotating. The illumination from the sun changes. So we end up tracing a line longitudinally across the satellite. And so the brightness change that we see with time, or in this case with phase angle, gives us information about the geometry of the surfaces of the satellite and its solar panels, and possibly also its behavior if the satellites are maneuvering or moving. And so we can see here that we've got these 5 curves up the top, which are all quite different, but show similar behaviors, and that you have kind of these broad peaks. And then we've got this magenta one, which is relatively flat over the full night. And quite, just immediately from this, we can see that there's something different between these 5 and this one. And indeed there is. So the magenta one, which is Meteosat 11, is one of these cylindrical spin stabilized satellites. So it has very little change in aspect as the sun position changes relative to it. And so its brightness stays relatively flat across the night. Whereas the other 5 are all box-wing satellites with solar panels that track the sun. And so we get these characteristic peaks that correspond to the specular reflection pattern as a function of angle for the reflection of sunlight off the solar panels, which are then augmented with additional bumps and wiggles that correspond to reflection or shadowing from other components, which are different from satellite to satellite. The other feature that's worth noting here is that there's a big gap in the middle. And so what this is because we are observing quite near the equinox, the position of the sun is effectively on the equator. So you have the disk of the Earth blocks the sunlight, and as the Earth rotates and as the satellites rotate, or it's more easy to think of this as the sun rotating around us, the shadow of the Earth sweeps across the geobelt. And so the satellites get cast into darkness, there's no sunlight to reflect, so they disappear. And then they come back a little over an hour later. Now, if we zoom in a bit more detail, we can see that some of these light curves have a lot of underlying structure. And to be able to see this structure, we really need to have both very accurate brightness measurements, but also very high time resolution. So once again, all of these observations were taken with 5 seconds between each measurement. And you can see here that this yellow curve, for example, has quite a lot of underlying structure. And the red one, which is NEV2, we can see does something kind of strange, which is started by this sharp peak, which happens and is all over and done with in less than a minute. So if you're only taking observations every 30 seconds or every 5 minutes, you're not going to see any of this detail, and you're going to miss a lot that could tell us about the structure and the behavior of these objects. Now, we can do one better than this for NEV2, because as part of the coordinated collaboration of Phantom Echoes, we also have access to telemetry from the spacecraft itself. So we know for a fact that this strange change in brightness coincides in time with the satellite doing a 180-degree roll maneuver. And so from that, we can kind of infer and say, well, we're seeing the light reflected mainly off the solar panels. As it does its roll, the solar panel angle to us is changing. And so we're getting less light reflected. And then as the roll completes, it comes back to its previous kind of aspect, because of course these solar panels are tracking the sun. So its relative angle ends up being the same to us. And yeah, it's goes back to its previous state. Now, that's all well and good. What else can we understand from this? So far, we were just looking at the light curve over a single night, and that gives us a single kind of one-dimensional slice longitudinally across each of the satellites. If we look at how these individual light curves change over a timescale of days to weeks, the latitude of the sun changes, because obviously as the Earth rotates around it with this axial tilt, the relative latitude of the sun to the satellite changes. And we are effectively tracing out a different longitudinal slice over the face of the satellites. And so if you stack plots of the light curves together like this, we effectively start to build up a two-dimensional plot of this that can be correlated to the structure of each of the individual satellites. And additional features that were visible but not really clear what they meant in a single night, we can start to get more intuition about. So we see here at around 0 phase angle a broad peak, which matches what we expect to see from spectral reflections off the solar panel. We also see very sharp increase in brightness around the peak, which we can infer is probably related to additional reflection of antenna or other structures on the body of the spacecraft. We also see the sharp step at the same position at about 90-degree phase angle night after night. And so this corresponds to where we're viewing the solar panels edge on. So there's a 90-degree angle between the sun, the satellite, and us. And once again, this is a feature that's known to happen as you kind of flip from the front face to the side to the rear face of the solar panels. And then for this satellite 4-7, we see on this kind of latter half of the night, the western phase angles, we see that there's these dips that are in a different position from night to night. And because of the way that we define the phase angle and line them up, they're designed around lining up features that track the sun. So when we have these features that move from night to night, it suggests that these are something that aren't tracking the sun, so is related to features on the body of the satellite, which holds a constant angle relative to the Earth, of course, because these things have communications arrays that need to be servicing specific areas. If we then compare this to 4-6, which is right next door, and is once again a similar box-wing satellite, we see the broad structure is the same, and that we have these broad peaks around 0 phase angle. We get some sharp increases, and we also have the 90-degree solar panel step. But there's a couple of extra features that we see here that we didn't see on 4-7. The first is that we get this enhanced bump, which moves to earlier phase angles over the course of the observation sequence. And I'll come back to this in a few slides' time, because this is quite interesting. The other interesting point is that on this western face, rather than seeing dips, we're actually seeing sharp enhancements in brightness that are changing on very short timescales. And once again, change from night to night, which suggests that it's associated with a feature on the body rather than on the solar panels. So we can then put on our thinking caps and say, well, how can we relate these differences to what we know about the physical structure of these satellites? So we can look up pictures of these before they are launched on the internet, and we can see a couple of details that I believe explain these differences. So 4-7 is shown here packed for launch. After it goes up, these communications dishes fold out kind of tangentially to it. 4-6 is similar. This dish up here is folded away, but actually full launch, it is folded against these strut structures. And then after launch, it sticks out like I'm showing with my cursor. But these strut structures are still there. And so we can kind of assume that maybe the shadows that we see are corresponding to these dishes on 4-7 shadowing the light that's being reflected, whereas the short, sharp, very spiky reflection behaviors that we see on 4-6 are likely to be due to augmented reflections off these shiny gold struts on the side of it. So then we can move on to MEV2 itself, and we see that its light curve behaviors are very chaotic over the first few weeks of our observations. And this is due to the fact that it's flying about, it's actively doing maneuvers, it's changing its orientation, you know, as it flies around, takes images and everything, does tests. So it becomes very difficult to say anything from these diagrams the same way as 4.6 and 4.7 could. But in this case, because we do also have the telemetry from the spacecraft, we know where it is and what its orientation is. So we will, over the, you know, one of our future research goals is to actually start to build theoretical models to simulate what we expect the light curves to look like. And we have an amazing data set to validate and test those models. So this is actually more exciting to me, even though it doesn't look as nice for the future prospects. Then if we have a look at Intelsat 1002, there are several more things of interest. The first immediately noticeable difference is that whereas the other satellites had their solar panel kind of glint peak centered near 0, Intelsat is closer to 30, and it's not single peaked, it's actually double peaked. And so from that, we can infer that this satellite, for some reason, has its solar panels offset by about 15 degrees. So rather than tracking the sun directly, it has the panels offset. And actually that the north and south solar panels are slightly oriented differently. And in fact, if you go back and have a look at some of the images and videos that MEV took of Intelsat before its docking, you can actually see that the north and south solar panels are aligned, offset, feathered slightly relative to each other. And then because this is offset, we see the 90-degree solar panel edge bump is actually shows up early in the night, 90 degrees earlier, whereas the plus 90 degrees is pushed past sunrise in the morning. The next point of interest is that we can see that the orientation of the solar panel offset does actually change gradually over time and not consistently. So here we can see it slowly creeps to larger angles, but then there was a period of a few days where it actually moved in and then suddenly reset. And we believe that this is due to the way that the satellite operators use the solar panels to kind of like a solar sail. So using the solar radiation pressure to help offset one of the degrees of freedom and keeping it stable. And so as the solar radiation pressure changes, they may need to change the orientation of the solar panels to counteract that. And the final change is that after MEV2 docks with Intelsat, we see a very large change in the overall kind of morphology of Intelsat. Whereas previously it looked like this, and we have data going back to 2018 that shows that it is very much the same. Whereas afterwards, we see that this double peak structure at 30 degrees disappears, and we now have it more like a traditional kind of 0-degree phase angle. So from that, we can infer that whatever reason that they had the solar panels offset relative to the sun must have gone away after MEV2 docked. And so they reset them to be more directly sun tracking. So that was all kind of single color, broad optical photometry. Things get more interesting when we look at how things change spectrally. And so to investigate this, we got some time using the GoTo North Prototypes Telescope, which is another project that we run from University of Warwick with facilities on La Palma. So GoTo is an astronomical survey telescope designed for following up gravitational wave triggers. So it's a very wide, very deep survey, which is a consortium of a number of universities and institutions. And so we were very lucky to be able to apply and get some kind of prototyping research time for this project. And so this is what the prototype telescope looks like. This has now been replaced with the final kind of production telescope. But at the time, we used the Central 4 telescopes with color filters. And so we were taking advantage of the fact that GoTo was designed to have a very large footprint. So it would mosaic multiple fields of view together to give a single larger field of view. But there was a small overlap between adjacent telescopes. So we can go in directly to the control system for the telescope and kind of intentionally break it so that each of these telescopes was observing a different color filter, whereas it's normally designed to use the same filter in each. And by very accurately aligning the telescope along the geobelt, we can position Intelsat and MEV2 into this overlap region where we get simultaneously each of these 3 cameras observing it in a different color band. And the other objects along the geobelt along this band where we have 2 overlapping. So we can get simultaneously 3 colors of these 2 and simultaneously 2 colors for the other 4. And then by alternating colors in different cameras, we can build up the different color pairs and cross-calibrate and do a whole bunch of things to get very nice looking data out of it. And so from this, we can compare and measure the relative colors of the different satellites. And we can see that they separate out quite nicely. So we have, so this tells us that we can effectively, without necessarily having the positional or brightness information of the satellites, we can identify them just from their color. And this is very useful when you have these proximity operations, because if you've got a satellite that's actively maneuvering and you don't have an up-to-date accurate orbit, there can be confusion and you don't know which is which. And as we saw with these light curves, the brightnesses of different satellites can change significantly during the night. And even here, there are some times where MEV2 is brighter than Intelsat, even though most of the time Intelsat is a factor of 10 brighter than MEV2. So at a single instance of time, you can't even be sure based on just the intensity. And you have to observe over a range of time and wait and see what the phase light curve behavior is doing to accurately distinguish between them. And so color gives us an interesting prospect to kind of break that and more quickly be able to distinguish between different objects. Now, because we were taking these observations over a short window of time, this was making the assumption that the colors were constant. And I discarded any points where that wasn't the case. But actually, a few of these observations did show color changes within the half-hour window. And specifically, we saw that this start of night bump in the Thor 6 that changed position as a function of time, we saw that this is actually associated with a very sharp blue glint. And so this is a very clear indication that this feature is associated with an off-axis glint from the solar panels. When you look at the BRDFs of solar panel material, you do see that you do get at specific angles these sharp blue glints. And so that lets us identify that feature as being associated with that structure. And it comes into the whole thing about identification and characterization. Whereas these very sharp peaky structures are not associated with any color change. So the red, green, and blue color channels all changed by the same amount. And that is more consistent with the insulation covering. And then finally, we also looked in more detail at the glints of Intelsat before and after docking. And we see that actually these main glints also do not show any significant color changes over the course of the glint. which again will help with our characterization, we hope, but is not enough yet. We really need more color light curves, more high cadence, and more objects. And so kind of building on this, this started with a talk that I gave at the Precision SSA workshop for GNOSIS here in 2020. And I kind of finished that talk by saying that color observations are a very likely avenue of interesting research going forward. And then this opportunity to look at Intelsat and the MEV2 let us kind of prove that concept and come up with some initial ideas. So I was able to combine those and put together a proof of concept application to GNOSIS, which was awarded. So that has given us some funding that we're using to buy an initial set of new detectors, which we're combining with some additional funding to upgrade the mount and my own time to do a complete overhaul of the telescope software. And so this is going to give us a very good capability using SuperWASP's very wide field of view to get simultaneous 4-color light curves of everything visible at GEO, so a couple of hundred objects. And we're expecting, fingers crossed, to get some very interesting results that I'll hopefully be able to talk about in a year or so. And that's all I had. Thank you very much.
Thank you for that, Paul. And again, nice to see another success story in terms of GNOSIS funding going to good use. Do we have any questions from the floor? I see Ben's got his hand up if you want to take the floor, Ben.
Yeah, just a quick one. Maybe I missed it, but what causes the specifically blue glints as opposed to glints in the other colors?
So it has, my understanding is it has something to do with the structure of the wires embedded in the solar panels. But in general, it just comes down to, different materials have got different reflection properties. For a lot of things, it's just kind of the subsurface scattering. I don't yet have enough understanding of the material science of this. But this is something that I'm hoping to be able to spend more time on going forwards and hopefully build up more expertise on.
Okay, so you should be able to even decide what material is reflecting.
Hopefully, yes. Well, for some materials, I think most materials don't have the specific sharp changes in reflection as a function of angle. They're a lot smoother. But yeah, my understanding is that because the solar panels are quite a complicated material structure, you do get these weird behaviors that makes them easier to identify.
Okay, thanks.
You're muted, James.
Sorry, yeah, just noticed. I see Stuart's got his hand up as well, if you want to take the floor, Stuart.
Thanks very much, James. Cracking presentation, Paul. Thank you very much. Some of the images that came back from ExoAnalytic of the unfortunate Intelsat 29E appeared to show it sort of venting stuff. I don't know the duration of their exposures, but I was wondering whether if a satellite is deliberately maneuvering and expelling a plume of propellant, is there any chance that you might see a reflection signature associated with that?
So that is a question I have asked myself, and unfortunately this data isn't quite good enough quality. The pixel scale is not great for this. But specifically, I was wondering if this peak here could be associated with venting like that from a maneuver, because otherwise it seems slightly improbable that you would have kind of the satellite sitting at a position where just a very slight change in angle causes a big glint. And so it could be that this corresponds to a transitional change as well. But on the other hand, I'm not familiar enough with MEV2. Like, I know that its main thrusters are electric. I don't know whether it has chemical propulsion. If it doesn't, then obviously not. You might be more familiar with that than me, actually, Stuart.
Well, I mean, I'm aware that satellites use different propellants, and the density and thrusts associated with chemical ones, I think, you know, one's initial intuition is that you stand a better chance of seeing that sort of material. But going back to your point about, you know, using color, I believe that most electric propulsion systems, at least at the moment, are using xenon, and that's a gas with particular characteristics and emission lines. And, you know, so it did lead me to wonder whether, you know, you might see a particular color associated with certain events that might, you know, reveal the nature of the propellant being used when it was being used.
That's very interesting. And I think, like, again, we don't have enough data with this data set, but hopefully if everything goes to plan with the SuperWASP upgrade and observation campaign, at that point, we will have enough data to start answering those questions. You know, 45 nights of 6 objects is still quite a small data set, but hopefully once we get 200 objects over a few months, we'll start to see a lot more interesting and possibly unexpected behaviors, which we can hopefully relate back to things like this.
That sounds really great. Good luck, Paul.
Thanks.
Okay, thanks for that, Stuart. Any other questions for Paul?
So Simon just clarified that it does have chemical propellant. So yeah, so that peak could possibly be due to that. Once we dig more into some of this truth data, we might know for sure whether or not that does correspond to that.
Is there a plan for an MEV3, Paul? Do you know any progress with regards to
So
that?
my understanding is that there is no official MEV3. There is a third mission that is not doing the same thing. It's the same kind of spacecraft, but doing something different. But I think the idea is more that, you know, MEV1 and MEV2 will be able to service additional satellites going forward. You know, once their contracts with Intelsat end, they can drop them off and then be reused for at least another cycle. So I think at the moment there's probably no plans, but I don't actually know. That's something you'd have to ask them. Entirely
fair. So yeah, I think that's the end of the questions for that talk. So thank you very much again, Paul.
Yep.
And I'll hand over now to our next speaker, who's Klaas Wiersema from Lancaster. He'll be talking about the final installment of this chapter on the MEV2 project, which will be talking about high cadence optical imaging polarimetry of the geostationary satellites we've been discussing. So I'll hand over to you, Klaas, if you're ready. That looks good to me.
Okay, thank you very much. So I'll be talking a little bit about imaging polarimetry of geostationary satellites, and particularly about the docking of MEV2 and Intelsat. I work at Lancaster University, where I'm an astronomer. So usually I study polarimetry of cosmic objects, but I do quite enjoy looking at satellites instead, because they show a very rich phenomenology in polarization space. I seem to be, there we go. So let's first recap very briefly what polarization is again. So polarization is a non-randomness in the electric field factor of the incoming electromagnetic radiation. So if the emission that you receive is unpolarized, there will be no preferential direction of the electric field factor. If there is, then it's linearly polarized or circularly polarized, or both. Now you can combine those things into a polarization ellipse, such as is drawn on the left side here, where you can see the electric field factor. In this particular case, this wave would be partly linearly polarized and partly circularly polarized. Now, circular polarization tells you roughly which way around you go the ellipse, clockwise or counterclockwise. And the linear polarization tells you the shape of the ellipse, the indentation of it, if you like, and its orientation with respect to your coordinate system. Now, in astronomy, we usually use the Stokes prescription of polarization. This is invented by Stokes. You see his picture there on the right, looking very happy with his discovery. So the Stokes prescription describes the polarization state as a vector consisting of 4 components, I, Q, U, and V. And I know that in some sciences they use a style of S0, S1, S2, and S3, but it's equivalent really. Q and U encode the linear polarization, and V the circular polarization, and I the total intensity. Now, those you can relate back to the polarization ellipse via a couple of equations that you can see over there. And one of the reasons why Stokes invented this is because this prescription allows you to use matrix operations on the Stokes vector to describe the effect of your optics or radiative transport or all kinds of other things that may influence your polarization state. So it's a very convenient thing to use. So why do we expect to see polarization at all? Well, the quick thing there is that the process of specular reflection, so mirror-like reflection, induces linear polarization. Now, if you now consider a wave reflecting off of the surface, then the electric field components parallel and perpendicular to the plane of incidence have a different index of reflection, a different reflectance. This comes from the Fresnel equation. So I made a quick plot there on the right, where you can see those 2 components for a reflection of water. As you can see, at very small incidence angles, they have those reflectances are almost the same, so you should see almost no reflection. Then there's a maximum where they're most different, which is around 55 degrees or so here. That's called the Brewster angle. So you'd expect the polarization of a reflecting body to be maximum at a certain angle. Now, the actual amount of polarization and the polarization angle as well that you detect from reflected signal depend on the refractive indices of the reflecting material, on the reflection angle, of course, or in other words, the orientation of the reflector, and the polarization state of the light before reflection. Now, we all know that sunlight is largely unpolarized, so when sunlight reflects off of a satellite back to you, the initial polarization will be almost 0, and the polarization is induced by the action of reflection. Now, I just want to give an example here what we can quantitatively do through from an example from astronomy. So on the right here, you see a sort of a diagram of a telescope. In yellow is the path of the light rays. They reflect off of the main mirror at the bottom and go to the secondary mirror, labeled 1 in this diagram, then back to a tertiary mirror, which is under a 45-degree angle, as you can see, which bounces the light to an instrument platform here labeled number 4. Now, in this situation, if your instrument on that platform is a polarimeter, you'd expect to see quite high values of polarization, because after all, the angle of the mirror here is about 45 degrees. As we saw in the diagram earlier, a lot of reflection angles, you should see large amounts of polarization. And indeed, we do. So this is a data set that I gathered from an instrument on the New Technology Telescope in Chile. Plotted at the top are the Stokes Q and Stokes U values. Where the dots here are the Q and U measurements of unpolarized objects in the sky. These are white dwarfs to be exact. And overplotted there in solid lines are a model that I've made for the action of reflection from the tertiary mirror. Now this tells you already that we can use our knowledge of how reflection works to predict what the polarization should be as a function of both the refractive index of the reflecting material and its orientation. Now, to expand on that a little bit, what we really do here is that we try to capture the behavior of the instrument and the telescope into a matrix chain called the Müller matrix chain. So this matrix here consists of the product of matrices that each describe the reflection of the mirrors and the coordinate transformations and rotations, all the different actions that take place in the instrument and the telescope. And then your detected Stokes factor S prime is the product of the total Mueller matrix and the incoming Stokes factor, which for sunlight would be unpolarized light. Now, the dominant component for instruments like this is the tertiary mirror that I've shown you before. Now, the individual elements in this matrix are really long equations containing the complex refractive index, which consists of a real and an imaginary component, and of course the reflection angles that play a role here. And then we can fit this matrix chain directly onto our data and leave the refractive index and the orientation as free parameters and retrieve those through a Monte Carlo-like fit. Now we can do this for satellites as well, of course. So if you get enough polarization data as a function of reflection angle, then we can fit for the refractive index of the reflecting material and also the orientation of the reflecting component. Now, of course, satellites are not nice mirrors. They consist of lots of different components that can each reflect, solar panels, the bars, all kinds of things. So this matrix is going to be quite large. There's no reason not to try, right? Now, of course, we need high quality observations to try this. Now, just as a quick illustration of what happens, I've shown you the Mueller matrix at the bottom, a reflection at 0 degrees. Now, as you expect, at 0 degrees should not be any induced polarization. And indeed, the matrix only has diagonal elements. And all that has happened is a small sign change in Q and V. Sorry. Now, at 45 degrees reflection, which you can see at the bottom, this is a very different story. There's loads of induced polarization. And of course, we also get crosstalk. So crosstalk is where incoming Stokes Q and U get converted to Stokes V and vice versa. So you lose some of your linear polarization to circular and some circular to linear polarization. It often turns out that this is a very sensitive thing to determine the properties of the reflecting material. Now, I should add here also that there's, of course, other groups doing this for satellites as well. Now, we have a new instrument in the UK that we can use called PopTop. It's on the Liverpool telescope. The Liverpool telescope is a robotic telescope on La Palma. It's one of the Canary Islands. And it's owned and operated by Liverpool John Moores University, with significant fraction paid for by STFC, which then doles out observing time that you can request. Now, it's a 2-meter telescope, which means you get good data with also when the source is faint. So lots of photons. This is what you need to do polarimetry well. It's able to track non-sidereal objects reasonably well if they're not moving too quickly. And of course, it's robotic, which means that your observations don't really impact too much on other people's observing programs. MOPTOP is a new imaging polarimeter that's installed there. What is quite fun about it, has a continuously rotating half-wave plate. It's 2 speed settings, fast and slow. In fast mode, each rotation is done in 8 seconds. And in slow mode, it's 80 seconds. But the light, when it passes through the half-wave plate, then passes through a polarizing beam splitter, which splits the light in an ordinary and extraordinary beam into 2 separate CMOS detectors, are completely connected to the plate sensor, which means that they are read out at times fixed by the position of the wave plate. And the data are ordered at n times 22.5 degrees. So in other words, you get 60 measurements for the full rotation. Now you only need 4 to make a measurement of Q and U. So it also means that you can get 4 independent measurements for each full rotation of the wave plate. And in fast mode, you can get a time resolution of 2 seconds, which is pretty quick. Now we look at the docking of MEV2 and Intelsat. Now you've seen these pictures before, of course, these from space on the right. You see that there are several reflecting components, the solar, the antennas, and the bus, of course. And it's, of course, interesting to see what they look like in polarization space. So our aim was to acquire dense polarimetric monitoring in 2 filters, blue and red, B and R, to probe the wavelength-dependent polarization during maneuvering, pre-docking, and the docked spacecraft afterwards, and to test the feasibility for a full matrix fitting in the future. Now here's some of our data on the left, and in the middle you can see the 2 spacecraft still separated, MEV2 and Intelsat. On the right they are docked. I'm happy to say that in all the cases that we acquired data, the sources were well within our field of view, which is quite good. This is our timeline of observations. You can see a big gap, unfortunately, on the left-hand side. This is where we had a major with the filter wheel that broke on mop-top, which unfortunately was difficult to fix because of the pandemic and access restrictions to the observatory. So we lost a fair bit of data taking there. Now, as you can see, we have about 10 or so observations before docking, and about 14 post-docking. Then, oops. Apologies for that. So before the docking, you can see some of our data here. So in blue is MEV2, and in red is Intelsat. You can see this is observations taken at about 30 degrees or so phase angle. And as you would expect, at 30 degrees, we're quite a way away from zero phase angle. There should be a net polarization, which you can see in Intelsat at about 2-ish or so %. And for FE2, it's about 5% or so. So they're quite different. A little bit later, at about 50 degrees or so angle, here we can see that the polarization of Intelsat rose considerably, whereas MEV2 declined a little. You can also see the scatter of the data points in MEV2 has increased quite a lot because it became fainter. Now, I wanted to briefly show here again the free inner sequence. So we start off with quite high polarization for MEV2 here at small phase angles and low for Intelsat. Now this matches the light curves quite nicely that Paul showed earlier with the different orientations of the two spacecraft during these maneuvers that they did in the beginning. So we can see here that the main source of reflection, the different orientation. Now, then I wanted to briefly, if I skipped a slide, apologies for that. Post-docking, when the two spacecraft are docked, we get something like this. So these are all measurements taken on the 22nd of April. Here you can see horizontally the time and vertically the linear polarization. Now, as you can see in bold are the phase angles. We can see here at the low phase angles, the polarization is low, as we would expect. At higher phase angles, the polarization increases. You can also see that this is asymmetric around zero phase angle, which matches with what we see from the light curve seen by Paul. Now, we also retrieved the same thing that Paul said about the offset of the angles of the solar panels in the before and after docking. We see that's back in our polarization data as well. Okay, so then we took a brief exposure of 4.6, which is the spacecraft that Paul showed earlier with all the glinting activity going on, to see if we could use mop-top to constrain where that glinting comes from. Now, this is the light curve that he showed you earlier, where you can see this nice smooth behavior at small phase angles, and then a massive amount of small glints at larger phase angles. Magnified in the bottom plot there is the light curve at the times of polarimetry. So we cover with our polarimetry a couple of these really large bumps. And this is what our polarimetry looks like. So in the top plot, you see the linear polarization in percent. In the bottom plot, in the middle plot rather, the angle in degrees. And in the bottom plot, the optical flux. Now, what's quite remarkable here, at least in my view, is that these very strong bumps that you can see in the light curve do not correspond to significant features in the polarization space. So whatever is glinting here is not really making its presence known very well in polarization space, which is quite interesting. Because the source was very bright, this glint was very bright, we get very small statistical errors, and we can constrain any polarimetric excursions to better than about 0.3% or so. Well, this is a single 800-second exposure, so we only cover about 3 and a bit degrees in phase angle. So it's clear that if we really want to understand this system better and model it, we need to observe with more data, really, which is the next step forward. So we've got a big campaign on 4.6 coming up in the next few months with MobTop, where we aim to boost our statistics on short time scale glints and also get the high cadence monitoring of the out of glint behavior to model with our matrix models. One thing we're going to try as well is to obtain polarimetry simultaneously from La Palma with LT and from the UK with the LE2 pole, which is an instrument I built a few years ago, which you can see on the picture below. Now, observing at the same time from La Palma in the UK gives you about a 5-degree or so different viewing angle, and that should translate into quite noticeably different polarization behavior. And this would really break many degeneracies that we might find in our Müller matrix models. So that would be quite exciting. Another thing is, of course, that we've got some data from a year ago, some data this year. We may be able to see some effects of aging. This is in fact what we do for telescopes on Earth with our polarimetry data, where we can see the clear changes in the reflective properties as a function of time. Of course, whether that is also visible in space-based reflective panels, we will have to wait and see. One thing that would be very interesting to try in the future is to test for the presence of circular polarization, in particular to measure crosstalk. Now, for that, you need illumination by linearly polarized light. The sunlight, general sunlight, is usually unpolarized, but there are moments at which polarized light illuminates a satellite. For example, if it's illuminated through Earthshine or by light refracted by the atmosphere just before it goes into the Earth shadow. Those would be moments where it might be interesting to test for these crosstalk effects. Now, and I think I'll end there. Apologies for the slight interruption in the middle.
Thank you very much, Klaas. That was very interesting, and excited to see where those observations take the project in future. Do we have any questions for Klaas in the chat? I don't believe so, but if so, please raise your hand.
I have a question, but I can't find the raise hand button. So
yeah, go ahead, Paul.
Klaas, could you comment on like the types of science you could do? Like, could you do the same type of thing with an LE2 pole class instrument on, say, a half-meter class telescope? You know, say it's in La Palma rather than in the UK. Like, at an instrumentation level, how much do you need something like MobTop versus a smaller, simpler, cheaper instrument?
Yeah, so where it really helps, so polarimetry is photon hungry, right? You need to get very high signal to noise detections to measure the required levels of polarization. And of course, satellites in some parts of their phase angle range get pretty faint. So with a smaller telescope, you then quickly run into cadence issues, where your cadence becomes quite slow. And you may miss out some of the fun stuff that you saw 4.6 or in some of these other satellites where a shorter time scale behavior shows up. Of course, any sources that have small bits that glint, they make small, they small components, if you like, you may under-resolve those and then get poor measurements out. But that said, there is quite a lot you can still do with poorer cadence observations. So some of these base matrix modeling efforts would probably work just fine with a poorer cadence, but you will then miss out on some of the perhaps more exciting bits that are present at the shorter time scale and at higher signal to noise.
Okay, thanks.
Thanks for that, Paul. I think in the interest of sticking to schedule, we'll move on to the next speaker. So thank you very much again, Klaas. And we're delighted to be joined by Thomas Schildknecht from the Astronomical Institute at the University of Bern. He'll be talking about observing and characterizing space debris. So very much looking forward to this. Thanks, Thomas.
Thanks a lot, James, and thank you for having invited me to give that talk. Let me try to share the presentation. I hope you can see my presentation.
That looks good to me, Thomas. Thank you.
Thanks a lot. So I'm going to talk to you today about observing and characterizing space debris in a more general way. And I intentionally, call it space debris here, because we are concentrating mostly on non-active, let's say, objects in space. And yes, we think that this type of research is going to provide the scientific foundation for sustainable use of outer space. In particular, we need to know more about the space debris environment when it comes to, let's say, guidelines for mitigation or even remediation of the outer space environment. So what do we know? And I don't think that I need to talk about this slide here. We know something like that there are 35,000 objects out there larger than 10 centimeters. Many of them we know by name. We have them in orbital catalogs, but there's probably more out there which we don't know right now. If you go for smaller sizes, there is estimates that there is twice the number of objects out there. And if we go for 1 centimeter, we are talking about roughly 1 million objects. And just keep in mind that the 1 centimeter object, when it collides with your payload or your asset in space at the given velocities, this is going to release the energy of a hand grenade. And that's the problem of space debris in general. So the question is really, why should we care? And the talks we have been hearing today, I mean, they're aimed at the particular, let's say, category of, let's say, for example, owner-operators or governance entities, while I think there is much more than that. So, for example, there are owner-operators, and of course, they care about the safety of flight. They want to prevent collisions, traffic management, collision avoidance maneuvers. These are the topics here. And if you've got a contingency, you would like to know why. All these methods which have been presented today, most of them could be used to investigate contingency cases. For example, just to look if the satellite is still stabilized, 3-axis stabilized, if the solar arrays are oriented in a way as they should, and all these kind of things. Then, of course, spacecraft designers, they want to know more about the risk they face up there. Could they mitigate that risk by shielding, passive shielding? The mission analysts, they would also like to mitigate risk. So by optimizing their trajectories, for example, their orbits, launch conjunction analysis. And finally, government space agencies, scientists like myself, they're mostly interested in protecting vital space services or critical infrastructures, which many of them critically depend on the space segments. So long-term sustainable use of outer space is one important topic here. And of course, we need to know the evolution of this environment. So you see that depending on who you are, you have very different, let's say, requirements and reasons why you care. So doing space debris research, we have a whole series of questions we would like to answer. First of all, of course, we would like to know more about the population. So how many of these objects are up there? What's their size distribution? What's their orbital regions? What's the nature of the objects? In many cases, we don't know even the nature of small size debris pieces. We don't know if this is a piece of insulation material, if it's a piece of aluminum, a piece of solar cell, sources and sinks. Seems to be obvious, but the sinks we know is more or less, they're simple. I mean, it's atmospheric drag and it's our atmosphere. It's the only sink we know there, but the sources, We don't know all the sources up there. The obvious one is the launches, and then some others like breakup events, but there is other sources like aging outer surfaces of spacecraft, which are, shedding pieces of the outer surfaces, just as one example. So we need to know more about the mechanisms, about the physics, creation, evolution of the orbits, for example, and as well as the long-term evolution. And many of the talks today were, addressing one or another of these questions. For example, tracing back fragments to the source, to the event, in order to identify, for example, breakup events. That's a very important aspect or a very important method we need. What are our approaches? First of all, we search for the debris. So it's surveillance. And obviously, when we do this kind of surveillance, we do not only detect debris, but we also see, obviously, the active objects as well, and we keep them in a catalog, not because we are interested mostly in the active objects, but because we are interested in the debris objects, and we want to separate them from the active ones and also keep the debris objects in a catalog in order to be able to follow up them and characterize them. So this is why we need to determine objects. By characterizing, I really mean here physical characterization. So the main aim is really to know what are the objects' sizes, material, and so on. Not so much what's their operational capabilities, or even if an active object is involved, what's the intended application. Okay, so we use a whole series of sensors to gain these observations. The most important set of sensors are our known ones at the Swiss Optical Ground Station and Geodynamics Observatory, but this is not the only series of sensors we are using. So here a few of the telescopes, by far not all telescopes we are using. We are using on one hand, our own sensors, like the 80 centimeter telescope SIM-MAIN, which we use particularly for spectroscopy. We have a double wide field telescope. We call it the SIM-TWIN, 40 centimeter. This one, we use those for surveys in high altitude orbits, but also for simultaneous multicolor observations. We have a 1 meter telescope at the same site, which is shared between satellite laser ranging applications, including space debris laser ranging and optical observations, in particular light curves as well. And then our smallest telescope in Switzerland is a 20 centimeter wide field telescope, which we use to maintain a catalog of large size objects in the geostationary region and in high altitude orbits in general. A few nights every month, we are using the 1 meter ESA telescope in Tenerife to, in particular, search for very small size debris objects in high altitude orbits. So, as I mentioned, we are also using our laser ranger, both for the orbit improvement, but also for attitude determination. This is right now still a geodetic laser, which means it's not a high power laser, but even though it's not high power, we can use it for this purpose. And we are right now installing a high power laser on the same system to be able to range to what we call non-cooperative targets, which have no retroreflectors of smaller size. So what do we know? I just want to give you one example. What you see here on the left-hand side is a view from the pole on objects we know by name. It's the spacetrack.org catalog at a certain epoch, and you see the B heave around Leo, and of course the region which we call the geostationary ring. So this is the picture from spacetrack.org. And this is the picture if we add for that particular epoch, December 2019, fragments from our own database. They are color-coded in green here. And you see, it's really a different picture. So one source of information is not always giving you the full picture. So the green dots here, I mean, they stem, as you may know, from 3 particular breakups which happened during that year, which we followed up with our own sensors, but of course, in collaboration with international partners. So this is a series of images. I hope you see not just the stars which are trailing by, but also small dots. If in the original frames, you would see more than 36 small dots here. These are images which were taken only about 20 hours after a breakup. By the way, by the small size telescope here, it's the 40 centimeter, one of the 40 centimeter twin telescope. So breakups happen, and they happen more often than you would think of. They still happen several times a year, producing each of them many fragments, hundreds and even thousands of fragments. So we were doing for many years a survey for small size objects in debris pieces in GEO, but in general in high altitude orbits. And what you see here is the histogram of a long series of let's say survey observations. In red, the objects which are uncorrelated, which you don't find in any of the official catalogs, and in blue, the ones which you find in the TLE catalogs. What is obvious here that we have a large population of small size fragments, most likely in the region from, let's say, 15s to about 20s magnitude, astronomical magnitude. I indicated sizes here. Of course, in order to do that, I need to assume an albedo. We assumed 0.1 or 0.08 for the albedo, so rather dark objects. So the fall off at the right-hand side, which is indicated by the blue line here, is fully given by the sensitivity limit of our sensors. So we assume that this is not representing the real population, but the real population will probably grow even more for small size objects. So if we then come up with orbits for these objects, we have been seeing something which was really totally unexpected. What you see here is a diagram showing the eccentricity versus the mean motion. And for a GEO object, of course, you would have eccentricity 0, mean motion 1, mean motion in revolutions per day. But the red symbols here again indicate the uncorrelated objects, so not which you don't find in the catalogs. So this huge amount of objects here around mean motion of 0, but eccentricities, up to 0.8. This was something which we could not explain easily. And if we follow up these over time, and I hope the movie is working, you see that these objects move up and down in eccentricity. So the eccentricity increases, decreases, again, while the semi-major axis or the mean motion stays the same. So this was kind of a mystery for at least a few months until we tried to, or we determined area to mass ratio for these objects. And believe me or not, most of these objects have area to mass ratios which are huge, which are compatible, for example, with multi-layer insulation foil material, so more than 10 square meters per kilogram. And then it became obvious, if you do the math, you will see that the solar radiation pressure is able to change the eccentricity in this way we have been measuring it. This is also a sort of characterization, just by looking at how the orbit evolves, or what type of air to mass ratio we are looking at. Okay, yeah, we have been seeing a lot of light curves. This is a high resolution light curve, 67 frames per second CMOS of a LEO rocket body. And you see very interesting features. I mean, almost everything you see in this picture is not noise, is real signal. But still, you know, if we would like to know what's the rotation period now of this object here? Is it something if the order of 7 seconds, or is it twice that? Because these objects have a lot of symmetries, and you know, you need to know these symmetries, and you don't know if you see the same side. If you have a peak here, is that the same side, or do we have enough symmetries that the real period is twice or 3 times or 4 times what we would guess at the first attempt? So we need more information, and guess what we can use? Of course, colors. But before I'm going to show you the colors here, this is a series of observations where you see that even GLONASS satellites tends to have a light curve, which is very interesting, but I have to say this is an abandoned GLONASS satellite here. So this object is clearly tumbling, and we were very much interested in, let's say, the behavior of these objects when they were abandoned. Classical light curve using a CCD camera with, you know, sampling rate of 1 sample every 5 seconds. And I think Paul mentioned, this is not good enough to get a good picture what's going on. You will miss, you know, some of the glints, for example. Nevertheless, you know, if you have a periodic signal like this one, and you assume that this is not a totally stable rotation, but for a time frame of 10 minutes or 15 minutes, the rotation axis is not changing too much in inertial space, then you could do a phase, come up with a phase diagram, which is nothing else than using methods to minimize the phase dispersion here. And this is actually from the very same data. And you see now nicely the front, you can distinguish between the front side and the back side of this satellite. So the peaks you see stem from the solar panel, one is from the back side, one is from the front side, and the rest is mostly from the body of the satellite. We have been looking, or we have been observing these satellites for a very, very long period. And on the bottom left, you see a diagram showing the rotational period change over time. And what you see here is, you know, decreasing period, increasing period, decreasing period in a, again, more or less periodic manner. And we have been seeing something like this today in one of the talks, you know, about the Europe effect. And of course, this is Europe. On the right-hand side, on the top right-hand, you see the primary idea. This is more or less how these GLONASS satellites look like. It's a cylinder and 2 solar panels. And if these solar panels are not perfectly oriented the same way, I mean, this is exaggerating here, you're able to spin up and spin down the satellite. We have been using simulators to do that, which have all these effects included, in particular the ESA IOTA simulator, where we were involved in the development. And we can reproduce these kind of spin off and spin down just by modeling the radiation pressure effects on these satellites. Very interesting objects, very interesting long-term behavior. And, you know, as already mentioned, I think this, you know, it doesn't mean that these objects will remain in this stable spin up, spin down mode. They could turn into a totally chaotic mode as well. You know, why is this all of interest? It's of interest if you would like to go there and do either in-orbit servicing or active debris removal. Laser ranging. I mean, we do laser ranging mostly to improve the orbits because the accuracy of laser ranging is of the orders of millimeters in the single measurement. This is an example we did quite some time ago with Envisat, and you see Envisat is spinning still today. And if you laser ranging from a site here in Europe, you will see that the ranges, you know, behave in a sinusoidal way. And what you see is nothing else than one of the scatterer here moving around the center of mass of the object. That's one of the type of information we can gain. Obviously, at the same time, we can also acquire light curves. What you see here is on the top, in the top figure, you see residuals of the laser ranging measurements with respect to reference orbit in nanoseconds. So we are talking about a few meters here, and in the bottom a light curve. So the question now, how can you fuse these two types of data? This is one. One big question. We have different approaches to do that, and we have currently studies ongoing to really do a better job on data fusion of different data types like SLR and optical. So color photometry. Yes, color photometry is useful on one hand, could be useful to categorize different bus types as we have seen in GEO. It's not always, by the way, successful, but if the bus types are different enough, you may be lucky. But also in order to disentangle this or to solve this problem of ambiguity in light curves of these multiple symmetries. For example, if you look at the top graph here, you see a light curve or two light curves. One is in the blue and another one is in the, or no, one is in the visual, one is in the red. And if you look just at the light curves, it's perhaps not evident which of the minima, for example, stems from the top side of the cylinder of this upper stage and which one stems from the nozzle side. If we then come up with a color index, so that's the difference between the two colors here, which is plotted on the bottom, in the bottom figure here, then it becomes absolutely evident that one side, the top side, is having a completely different color from the bottom side of this cylinder. And again, this is, as some of the previous speakers have mentioned, this is an additional information you may use to characterize, in this particular case, the attitude state of an object. It could also be used to characterize, other details on the object of interest. The important thing to mention here is that we need absolute simultaneous observations because, as you see, there's a lot of signal in this light curve, and we're not. We really need to be absolutely simultaneous with the 2 or 3 or 4 colors in order to come up with a meaningful color index. If we go one step further, and that's what we do with our 80-centimeter telescope at Maine, we do spectroscopy. So we, in principle, it's nothing else than looking into a more detailed to more detailed color information. On the left-hand side, you see here a spectrum which we have been acquiring at two different moments, the red and the dark, the black line here. The x-axis is wavelengths in angstroms, the y-axis is just intensity. What you see here in this particular case is a telltale knee at about 500 nanometers. And we compared, of course, all these spectra with lab measurements. And in this particular case, the only lab sample where we could see that knee at around 500 nanometers was MLI material, either the space-facing side or the spacecraft-facing side, the blue and the red curve here. None of the other materials, being it different paints, bare aluminium, or solar cells, shows that distinct feature. So we are here pretty convinced that this is an indication that we have MLI material here. And by the way, this object here had a high error to mass ratio. We have other examples. For example, a bright geodebris here, really bright. Error to mass is low, only 0.04 square meters per kilogram, 12th magnitude. It's a large object, but tumbling. And we think we have been measuring two sides, the front and the back side, let's say, of this object here, in red and in black. By the way, the feature here around 780 nanometers, that's that's an artifact from not fully reduced feature from the atmosphere, from oxygen in the atmosphere. But the overall trend here is very typical for material which was exposed to the space environment, namely that it is very red. It's really red. If we have spectra, for example, from the Meteosat satellites, the classical GeoMeteosat satellites, which are spinning cylinders, which are mostly covered with bluish solar cells, they look even redder than this spectrum here. So material has a completely different color once exposed to the space environment than the colors we expect from lab measurements. Okay. I mentioned already, for example, for these breakup fragments, we have large collaborations with many different organizations, networks like the ISAN, the International Scientific Optical Network. We are operating a network of sensors together with the German Space Agency, DLR. We have close collaboration with colleagues from the Kalisz Institute of Applied Mathematics in Moscow. ESA, of course, is one of our main partners, but also CNES, NASA, JAXA. So international and global collaboration is key for all what we are doing here. So I think this is, it's contained in the acronym of GNOSIS, and that's why I'm so keen to see how we can really collaborate with each other in this context. Take-home messages. We need really collaborative, international, and holistic approach to address this space debris problem in exactly the same way as we need it to address the SSA or space traffic management problem. I mean, these are all different aspects of finally the same thing. We want to make sure that we can safely operate in outer space. And this type of research provides the scientific foundation for long-term sustainable use of outer space. And with this, thank you for your time.
Thank you very much, Thomas, and nice note to end on there. I know that certainly the GNOSIS management is very keen on looking into those potential collaborations and exploring those further. So yeah, I see Catherine's commenting as well, our chair of the steering board. Are there any very brief questions for Thomas before we move into a very quick break? Otherwise, we'll do so and then get on with the rest of the program. I'm not seeing anything come through. So I'll thank you very much again for your time, Thomas. And yes, we'll move into a very short 5-minute break now. So I'll adjust the timings on the schedule and then share the screen again. But we'll be meeting back at 22, so 16:40, and we'll carry on with the rest of the day's program. Thank you very much again.
Thank you, James.
Right, sorry, my mistake with the timings there. Was a little overzealous with the break time. So yes, as we said, 5 minutes. So hopefully most are still connected up. Yeah, just a quick note, because we've had several questions coming through regarding the recording. We are recording today, and the link to the recording will be made available shortly after the event. So that will hopefully be sent out either tomorrow or the day after, depending on upload time and so on. And you'll be able to catch anything that you miss on the day itself. So thank you very much to our speakers so far. I think in the interest of timings and sticking to time now on, we've got a slightly later end time now. If any of the speakers to come have any issues with their new times that have been published on this slide now, let me know and I'll try and rearrange things around if we need to. But otherwise, we should hopefully be able to stick to this. So I'll move on to introduce our next speaker now, who is Toby Harris from Astroscale. Toby's going to be talking about understanding SSA requirements for safe and successful active debris removal missions. So thanks for your patience, Toby, and I'll hand over to you if you're ready.
Great, thank you, James. Just share. Okay, so hopefully you can all hear me okay. I'm going to talk a bit about SSA requirements for active debris removal. I will skip these first two slides, as I'm sure most of you have seen these many times ago before. If you want to know anything more about Astroscale and what we do, then by all means get in contact. I'll very briefly whip over these sort of the key missions that we're involved in at the moment. So ELSA-D, which I'll talk about a little bit later, is our spacecraft that's currently in orbit. Also in development on the UK side is ELSA-M, which is going to be our constellation end-of-life services spacecraft. We have ADRAS-J on the Astroscale Japan side, which is an inspection spacecraft, and LEXI, which is our life extension spacecraft being developed by Astroscale US with support from Astroscale Israel. Okay, so active debris removal and SSA. So for here, I'm defining active debris removal as the removal of obsolete spacecraft, satellites and rockets, or fragments of spacecraft that have broken off satellites and rockets. Crucially, the use of SSA capabilities is essential to underpin ADR missions, and I'll go and explain some of that momentarily. As the population of space objects grow, we're going to need new SSA capabilities, including precision SSA, in order to track, identify, characterize space debris in the environment. And I think that was well described by our previous speaker in a lot more detail, so I won't need to speak about that now. What I would like to say is that there's four sort of key areas to ADR missions which require SSA. Mission planning, so in advance of the mission itself. The operational support, so that's actually using SSA during the mission to make sure it's successful. There's operational safety, so that's ensuring that the mission is safe, regardless of whether it's successful or not. And then the environmental analysis as well, understanding more about the environment and what's happening in orbit. So active debris removal is a subset of RPO, or rendezvous and proximity operations. So what do I mean by that? So a rendezvous operation here is defined as matching the plane, altitude, and phasing of two or more spacecraft. So here we're calling them the servicer and client. So servicer is the spacecraft that's going up to interact with the client. Proximity operations are where you're intentionally performing maneuvers to affect relative states. It normally happens in a much closer proximity than you'd normally get to another spacecraft. We're normally talking sort of tens or maybe hundreds of meters. And then docking, which is a subset of proximity operations involving physical contact between the spacecraft. And ADR is effectively a subset of this, where you're involving docking with a semi or non-cooperative space object. So what kind of SSA do we need for active debris removal? There's four main requirements that I've defined is needed for successful and safe missions. So first of all, the orbital state, the frequent accurate state data of all the relevant spacecraft and space objects. Almost goes without saying. Attitude dynamics, so the current attitude rotation rate, as well as the spin axis stability, and information to predict the future attitude rotation rate is really important. I'll talk about that in a minute. Collision avoidance, is essential to any space mission, both for standard operations, but also during rendezvous and proximity phases. And then the re-entry risk, assessment of the client's service at time and location of re-entry. And so we need to understand what kind of capabilities SSA can provide now for these, and what kind of gaps are there that exist, and we need to develop further on. So starting off with the orbit state of both the servicer and the client is essential for ensuring a successful mission. So when we're at sort of the orbit insertion phase, very early on in the mission, when the servicer is being inserted, we might be hundreds of kilometers away from the client, what I've sort of termed as pre-rendezvous, I guess. And at this point, the client would be, or the servicer rather, would be using GPS as a principal way of getting information about where it is and where it's going. The client is typically determined to be non-controlled and inactive. So for there, you're relying on SSA data, state vectors, TLEs, ephemerides, covariances, etc., in order to understand where it is and where it's going. As we move closer to the rendezvous phase and then later to the proximity operations, the distances close significantly. At one point, you can start using the onboard sensors in order to perform relative navigation. So you're no longer dependent on ground-based SSA to determine where the spacecraft is, where it's going. However, we've discovered it's essentially very important in order to have that additional SSA data to augment the information you already have on board the spacecraft, to minimize covariances and to have best idea of where the spacecraft is at any given time, as well as their relative locations as well. One thing I want to point out as well is for a RPO type mission, you end up maneuvering quite a lot, and you end up having maybe a number of irregular large maneuvers when you're sort of tens or hundreds of kilometers away. But as you move closer to the spacecraft, you're performing many maneuvers, perhaps getting smaller and smaller as the spacecraft come within proximity of one another. But what that does mean is that you need to have good frequent orbit determination to be performed after these burns in order to really understand where the spacecraft are and where they're going. So it's absolutely critical that you have good SSA, precision SSA to support these activities. Then looking at attitude dynamics or object characterization. Again, Thomas did an excellent presentation before this, going into some of the details of attitude dynamics through photometry and satellite laser ranging. These are key parts of planning and also during mission operations when it comes to active debris removal. Client selection is highly dependent on the object's dynamics, the client rotation rate, the rotation axis, and the stability in order to determine how that object might evolve in the future. In a mission planning phase, you might be doing these observations 2 or 3 years before the actual mission is launched. And so you need to understand how those observations might change over that time, so you know what state the client will be in at the time where you actually beginning proximity operations. And also the rotation axis, as I kind of illustrated on the right here, is really important in defining how the mission will proceed. If the rotation axis is along sort of the primary capture axis, as you can see on that diagram on the right, then things might be a lot easier than rather if it is rotating perpendicular to the primary capture axis. It makes it quite a different approach and potentially a different type of spacecraft that might need to do the activities. There's been a number of studies and activities to try and understand the environmental knowledge of attitude, rotation rates, and attitude dynamics of objects in orbit. This is something we would like to understand more of, and we would encourage more SSA knowledge available to do this kind of work. One thing in particular is looking at the rotation rate of objects in low Earth orbit. Typically, the rotation of these objects are limited, or their understanding of the rotation of these objects can be limited by the short duration of passes across ground-based sensors. And so you can see on this diagram on the left, you get this selection bias for the rotation rate of objects in LEO. And so trying to understand better what that distribution is and better what the sort of distribution of rotation rates of objects is going to be really important when we look at active debris removal in the future. So number 3 is collision avoidance. COLA is essential during all mission phases for any spacecraft mission. And this is no exception for rendezvous and proximity activities as well. And we need to be able to reflect conjunction assessment and screening when you're performing an RPO. In particular, when you're looking at 2 spacecraft moving towards one another, we need to be able to perform reasonable conjunction assessments based on sensible screening volume and also sensible collision cross-section, etc. So we need to have those kind of processes in place when we're dealing with determining potential conjunctions between two spacecrafts in close proximity. This is also really important when we're trying to determine the mission operations, when to perform docking and when to perform close proximity activities can be dependent on what's going to happen in the next few days in terms of third-party objects and any potential conjunctions. So having those processes developed and having that information available is really important. And then finally, should we need to perform a collision avoidance maneuver, you need to be able to account for two objects in close proximity. And then finally, re-entry risk, again, essential to operation safety on the ground, requiring assessment of time and location of re-entry. And typically for an active debris removal mission, we're looking at both the controlled deorbit of a joint stack, two objects connected together, but also of the controlled or partially controlled release and deorbit of the client object, should that servicer then go on to look at deorbit another object afterwards. And so here's kind of a sort of a summary of what we think sort of the main demands for ADR when it comes to SSA, looking at the different, what I call the SSA products and the specific objects involved and where that feeds into the different types of support, whether it be mission planning, operation support, etc. And just looking at some of the data requirements on the right there, we've tried to quantify some of the precision that we acquired, and I think this is still a learning activity at the moment to try and understand what is an acceptable level of precision to ensure the missions are safe and to ensure that they're successful as well. And so this is something that we want to try and explore more, particularly through our in-orbit demonstration missions like LCD. So here's kind of an illustration for what I call a two-client active debris removal mission. Looking on the bottom left there, we have the pre-launch, the planning phase, the kind of information that we require during that sort of pre-2-3 year phase before the mission itself. And then we move on to the LEOPS and commissioning once the spacecraft servicer is in orbit, inserted into its initial orbit. And then we look at the servicer reorbiting, so moving from that insertion orbit where it performed LEOPS into the first client capture orbit, and then deorbit and disposal of that first debris object or defunct spacecraft. And then moving on to servicer reorbiting again for the second client. In this case, we're also having a sort of a RAN drift phase where it changes right ascension to move on to the second client, at which point that would also be recovered and then disposed of as a joint entity. And these are all the kind of different points in the mission that we expect the different SSA requirements to feed in. So I'll talk a little bit about LCD. So obviously SSA support is key for any of these missions, particularly for LCD, and space safety is top priority for this mission. So we perform conjunction assessment and risk analysis, coordination with other spacecraft operators, and also data sharing quite regularly to ensure the safety of our spacecraft. Collision avoidance is supported by ESA, the 18th Space Control Squadron, and SpaceNav. And we've also got additional support provided through Leo Labs, who are providing on-demand collision assessment and proximity monitoring as well. So this has really been helpful in trying to understand and ensure the safety of the spacecraft. So just quickly, an update on where we are with LCD at the moment. As many of you know, it's currently in orbit in the midst of its second demonstration. We had anomalous spacecraft conditions, and so the demonstration is still continuing at the moment. The service and client were maneuvered to a safe separation of around 100 kilometers or so. Recently, we've been maneuvering the service into position close to the client, so it's about 25 kilometers safe separation. However, throughout this, we've been performing SSA observations of the mission throughout, trying to understand better about what kind of SSA gaps there are, where the precision lies, and what we think it needs to be in the future for similar sorts of missions. And so whilst it's still quite early days to do a lot of the assessment at the moment, we're still trying to use the information we have about LCD at the moment to try and understand some of these SSA needs. And as no doubt many of you on this meeting know, we've got quite a few observers who are involved in taking observations, measurements, and performing analysis. There's kind of a list of some of those players on the right-hand side there, which we're very grateful for the input of all these groups. And one of the things we've already learned quite a lot about the SSA issues for these kind of missions. One thing I was just going to quickly bring up here is the cross-tagging, actually. When we had separation of the client from the servicer, we had cross-tagging between the two spacecraft for almost 24 hours, where the spacecrafts were identified, well, not incorrectly, but they were switched around for a short period of time before that was corrected. And that was one of the issues that, that was interesting to observe during this mission, and something that we would like to explore more in the future to ensure that cross-tagging is minimized for these kind of missions. Okay, and that's pretty much it from me. So, like I say, precision SSA is absolutely essential to the safety of all missions, and RPO is definitely no exception to this. Active debris removal being a key application of RPO for removing objects in the future. Some of the SSA demands for RPO include increasing the frequency of observations for orbit determination and COLA, as well as new requirements as well, such as trying to understand the attitude motion, the rotation rate, the tumble rate, and the axes of rotation of defunct objects. And we're also still using LCD to help provide unique knowledge and insight to future SSA requirements that we need for these SSA needs. And I think that's all from me. Thank you very much.
Thank you very much, Toby. That was very interesting, and it's nice to hear some, I guess, quantitative requirements placed on some of the data products we've been discussing throughout the afternoon. I was interested with the cross tagging. Did that take place at a time where, you know, the onboard navigation wasn't able to help with that, so to speak, or because obviously that's slightly more concerning than if you know, you've got completely no idea which one's which, if that makes sense.
Yeah, I mean, the cross-tagging was really from the ground-based sensors that were picking up the objects rather than the onboard ones. I mean, obviously the onboard, we knew the telemetry of the spacecraft and knew where they were from that point of view. So it was really just from a ground-based SSA point of view.
And we've got a question from Ben, if you want to take the floor, Ben.
Hey, thanks for the talk. You mentioned looking at the tumbling rate for targets. Are some targets tumbling too much to ever be selected for removal, or do they just require different consideration?
I wouldn't say that some targets would be tumbling too much for future removal. I think there are very many different ways of trying to remove objects, different ways of trying to capture them. So you've got to be careful on what kind of technique you use, ensuring it's suitable as well. But there's also potential for detumbling objects in orbit as well. This is something that we're keen to explore in the future, because at the moment, some objects do look as though they are tumbling quite quickly. And so they might not be necessarily viable targets given the current technologies. And so it might be that you'd need to look at ways of reducing that tumble or accounting for it in some way. So.
Okay, thanks.
Thanks for that, Ben. So I've got a question in the chat from Leonani. Are you hoping that the demonstrations will help to reduce the very cautious servicer client distances shown in your orbit state slide, or will those be retained, do you think?
So assuming it's fell to D. So yeah, I mean, at the moment they are quite cautious, but they're obviously going to be getting smaller and smaller as we get closer to the spacecraft. I think at the moment we're just ensuring that everything's going correctly as we move into sort of the short range approach. So yes, it will be moving much closer than sort of 25 kilometers.
Okay, thank you very much again, Toby. I think that's all the questions dealt with for now. If anyone's got any other questions, then please stick them in the chat and we can address them slightly later. But thank you, Toby, again, and we'll move on to the next speaker, who is Massimiliano Vasile from University of Strathclyde. He'll be talking to us about robust orbit determination and hyperspectral imaging for space domain awareness with their Cassandra framework. So over to you, Massimiliano.
Hello and good afternoon, everyone. Can you hear me well? Yeah. Okay, so
yes, that looks good.
Yeah. Okay, good. So this talk is actually two different presentations that I tried to merge together because I realized that the workshop was interested in two different things. So one is more about robust and precise orbit determination, and the other one is on a project that is ongoing at the moment, and it's how to use hyperspectral imaging to characterize space objects. So starting from robust orbit determination, so let me explain a little bit what we have done in a couple of European projects. One is called Stardust, that is still ongoing, and the other one is called Utopia, that was all about treatment of uncertainty. So one thing that we did was trying to understand the nature of uncertainty that you have to deal with in, for example, orbit determination, but in general in orbital mechanics. And the other thing is how you can reason about uncertainty to have a robust understanding of the motion of objects in space. And the other aspect that I'm going to explain is this idea of nonlinear statistics, because in most of the cases, people tend to reason about mean and variance, but it might be a bit limiting factor in robust orbit determination. So the first thing is to understand that uncertainty comes in two different flavors. And at the beginning of this workshop, you heard about this. So one is so-called aleatory uncertainty, which is the natural randomness. And this can be easily captured through normal statistical distributions. But the other uncertainty is the lack of knowledge we have on, for example, space objects. And that is a kind of uncertainty that is not always that easy to model. So there are techniques to do that. For example, you can use sets of distributions, cradle sets, belief function, fuzzy sets, and so on and so forth. This is something that I actually started working on many years ago. I have here an example of a first attempt to use a particular theory that used belief functions to characterize trajectories. For example, in this case, I was trying to characterize the uncertainty in re-entry trajectories when you try to incorporate uncertainty in the atmosphere, for example. So at that time, there was not a lot of interest in using anything that was not just mean and covariance, but more recently, I noticed that there is a growing interest in characterizing uncertainty in a different way. So why is that important for orbit determination? Well, one thing that is typically done is you use Bayesian inference to take a prior, which is your estimation of the distribution, for example, of your space objects or the fragments or whatever. And then you want to obtain the posterior after you receive a measurement. Okay, so you have a model of the likelihood of that measurement, and then you normalize that, and then you calculate your posterior distribution. And this is the typical process that you have in Kalman filtering, for example. Now, the problem is that the distribution is generally something that might not be completely known because you have multiple sources of information. And then if you don't know the dynamics because you are not the ones who is doing the propagation, then you might have an uncertainty in the model itself. And then, of course, you have an uncertainty in the sensor because it might not be completely well characterized, or you can have multiple measurements and need to be data fused, or they might not give you the same kind of measurement. Okay? So probably where we have the majority of the epistemic uncertainty, so the lack of knowledge in a number of cases, is when you have multiple sources of information. And this might come from, again, multiple people observing the same object and giving you a different measurement. And in fact, this, from the experience that we have from different people providing conjunction data messages, happens also because you have maybe different covariance matrices that correspond to the same event. So how can we deal with these multiple sources of information? How can we mix this into a single robust estimation? How can we deal with the fact that maybe some information is missing? And how can we combine distributions that maybe are different in nature? Okay? And ultimately, how can we deal with maybe something that is missing in the knowledge of the dynamics of the object? Maybe we don't know completely the dynamics because we don't know if, for example, light pressure plays a role, or if the atmospheric drag is important in the future evolution of the orbit. So these are just some past activities that we did in Stardust. For example, we tried to understand the combination of aleatoric and epistemic uncertainty in the prediction of collision and the prediction of the re-entry time of objects in space. We extended this idea also to the impact of minor bodies with the Earth, because there is a problem of ambiguity in the characteristic, the physical characteristics of objects. And then we try to apply this to implement robust collision avoidance maneuvers, for example. But there are other examples of people that try to use theories that do not model this uncertainty just with a distribution. For example, this more recent paper on the use of plausibility theory. Plausibility theory is fundamentally similar to the use of belief functions. They're not exactly the same theory, but they belong to the same category of non-probabilistic or so-called imprecise probabilistic theories that deal with, for example, subjective probabilities. Okay, so they're very good at, for example, capturing the epistemic uncertainty that you have if multiple people are providing information on the same event. The other problem that you have when you try to do robust orbit determination is not just to understand the uncertainty in the measurement in your model, but is also that a lot of people put effort in trying to propagate uncertainty non-linearly using a lot of very interesting techniques. But then when it comes to determining the state of an object in the future, then all this nonlinearity is kind of lost because you end up using anyway a covariance matrix. And this is an example of the uncertain Kalman filter that is used in trying to do orbit determination. And you have a nonlinearity in the dynamics, of course, and the uncertain Kalman filter captures this in the propagation phase. So when you try to propagate the covariance, when you try to propagate the mean value of the state of the object, but then in the inference part, which is the calculation of the Kalman filter, then the model is again linear. Okay, so using a matrix, a covariance matrix to characterize uncertainty. And so this means that the distribution is of possible states of an object in the future is sort of always seen as a linear model with the mean and added Gaussian distribution dependent on a covariance matrix. So there are other ways that people try to solve this. One is using polynomial chaos expansions that give you higher order moments, for example. Other people use the Fokker-Planck equation or that is derived from the Kramers-Moyal expansion to propagate the entire distribution. You can propagate the entire distribution also using techniques implemented in standard particle filters. And other ways is to use kernel models like a Gaussian mixture model. So all these techniques are very good and can be used to not just propagate the state, the distribution of the state non-linearly, but also to propagate a multi-model distribution, for example. So one thing that we did recently was develop this filter that is implementing a lot of these techniques. So it's a robust Bayesian inference filter in which we use a fast propagation of all the possible states that derive from our knowledge of the dynamics and initial conditions and the measurement. We can do this with a polynomial algebra propagator or with a stochastic collocation. And then we use particles that are drawn from the polynomial model that we have propagated forward in time upfront to reconstruct the distribution of possible states. The interesting thing of the techniques that we implemented here is that we can account for epistemic uncertainty. So we can assume that we don't have a full knowledge of the distribution of the initial conditions. We don't have a full knowledge of the likelihood, for example, of the measurements. We may have multiple sources of information that we want to combine. And when you combine them, you might end up with a set of possible likelihood and a set of possible prior distributions. So once you have all this, what you can do, instead of having a single point estimation, you can calculate an interval around the possible states of the object. And if you need to calculate, for example, the probability of collision, you can calculate an upper and lower estimation on that probability of collision. And this gives a much more robust estimation of what happens to your object in the future, okay? Because it accounts for that level of lack of knowledge that is typical when you have multiple sources, for example. We're also using, again, Dempsey-Schaffer theory of evidence with belief functions to, for example, give different credibility to different sources and create a model of that epistemic uncertainty that might affect different measurements. So again, the loop that we implemented has a first propagation of all possible states. We build a model of the dynamics. The model is essentially a polynomial representation of all possible future states of the object. And then we use this polynomial representation to draw samples, to draw particles for our particle filter. Then once the particles are defined, we play with the weights of the particles, and the weights in a particle filter define the distribution. So by changing the weight, you can change the distribution of the possible future states of the object. And then we apply a very effective optimization loop with guaranteed convergence to maximum and minimum to calculate those bounds on the possible future state of the object. So this is the kind of loop that is implemented. The optimization plays on the epistemic variables, which in this case define the set of possible distribution functions that define the likelihood and the prior distribution of the object. So this is an example of how we, for example, propagate uncertainty with a polynomial model. So you start from an initial set of possible states, and then we generate all possible future state subject to the dynamics, and we can use a complete dynamic model with gravity, drag, light pressure, and so on and so forth. So we inserted this into the Cassandra framework. The Cassandra framework is a way for us to integrate many different tools that are useful to do space environment management. We have tools that simulate measurements. We have very good models for radar observations. And then there is a part of Cassandra that does state estimation. This is this RSE that use the particle filter that I just explained. And then this goes into our agent system, is an intelligent decision-making system that makes decisions on those robust state estimation and decide whether to allocate a new maneuver, new observations, or allocate a collision avoidance maneuver. Cassandra includes also a link to another tool that we have developed called Titan that instead deals with re-entry, fragmentation, and the footprint of a possible re-entry object. So in the framework of Cassandra, you have the observation that come in, and there is the particle filter that is estimating the future state of the object. And then a decision is made on the possible collision. And then, as I said, you can have either the implementation of the collision avoidance maneuver or the request for a new measurement and an update of the estimation of the future state. Now, the interesting thing is that the outcome of that estimation is something like this, for example. So on the impact plane, so on the plane at time of closest approach, you have, for example, your object here, and because you have multiple sources of information, you don't have only one covariance matrix. Okay, this could happen also if you receive from different SST providers different conjunction data messages. So what you can have is that on this plane, the possible uncertainty connected to an incoming piece of debris or two objects that intersect, so they have a conjunction, can be represented by multiple different ellipses. Now, and here there is an interesting thing, because what happens normally is that this ambiguity, this uncertainty that translates into many different ellipses is often captured by extending the variance. Okay, so you try to capture all this within a large covariance matrix. But this leads to a very known paradox that if you increase the variance, at some point your probability of collision goes down. Okay, and this is called dilution of precision, of probability, sorry, and is in fact a strange problem, because the less you know, the less basically you need to worry about a collision, which is counterintuitive, because instead the less you know, the more you should be worried about a possible collision. And this again due to the fact that epistemic uncertainty is not taken into account correctly, okay? Because it is considered to be instead an aleatory uncertainty, is considered to be a randomness in the process of estimation. So we avoid this by again using Dempsey-Sheffer theory of evidence and calculating that lower and upper measure on the possible probability of collision. So this is given by two values called belief and plausibility that again give you the upper probability that the object can have a collision and the lower probability that the object can have a collision. So the recipe for us is compute the probability of collision, then model your uncertainty and the different sources of uncertainty, the credibility of these sources, data fuse these sources, and then calculate the belief and the plausibility. And the gap between belief and plausibility tells you how much information you need to have an informed decision. So that sort of capture the lack of information that you have on the probability of collision. So this confidence interval is something that you can add to your decision, and instead of relying only on the probability of collision itself, you use the probability of collision and you add to that the confidence that you just computed on the correct value of the probability of collision. And this gives a much more interesting and informed decision on implementing a collision avoidance maneuver. So this is an example of use. So you take some measurements 48 hours before the time of closest approach, the estimated time of closest approach. Then the decision-making system noticed that there are many different sources, but there is not enough information there to actually make a decision, because a lot are not consistent. As you can see, there are many different ellipses that might not be consistent. So this requires another measurements. This is taken 24 hours before. And in this case, the second set of measurements give a more consistent set of ellipses. Okay, so in this case, the information gap, so that confidence interval becomes smaller, so we have more certainty in the correctness of the calculation of the probability of collision. At that point, we can trigger the calculation of collision avoidance maneuver. And after that, as you can see, this is the target, and this our uncertainty is moved away from the target, and every ellipse now is not intersecting the target, so we have a robust implementation of a collision avoidance maneuver. So these are some references that explain a lot of these techniques that we developed over the years. Some are recent, especially these ones. We use the same technique also to study retargeting maneuvers, for example, around Jupiter, when you have to do very close flybys. Conceptually, the problem is very similar because you need to implement a robust maneuver, knowing maybe very little about the state of the spacecraft. And these two papers here explain the implementation also using Dempsey-Schaffer theory that give those bounds, those confidence bounds on the probability of collision. All right, the second thing is how we plan to use upper spectral imaging. So this is a project that is ongoing, is something that we are developing as part of an STP grant supported by the UK Space Agency. We're working in collaboration with Fraunhofer here in Glasgow. They do the experiment in the lab, and we do the signal processing and the modeling of the objects in space. So the idea is, okay, you observe objects in space and you don't have an extended image of these objects, so you don't know exactly what they are. Maybe you have a stricter life, but you don't have an extended shape of the object. And from one pixel or a very limited group of pixels, you want to understand what the object is made of. And an idea is to use the same hyperspectral imaging technology that is used for example, observing asteroids, or vice versa, is used to observe the Earth from space. So the idea is to spectrally decompose the light and then try to associate, first of all, the decomposed light to the motion of the object, because you can now do light curve analysis, but by wavelength, rather than doing light curve analysis over the entire light that you receive. And you can also try to do material association. There is a caveat that I will explain later, but you can try to associate a material to the spectra and therefore identify which face of the object is pointing towards the camera. So I'm not going to show everything, but we developed a high fidelity simulator in which we can construct objects of different shape. For example, this is a T-shaped object. We can put materials of different sort of on each one of the faces, but also multiple different materials on the same face. And we can simulate the dynamics of the object. We have a couple attitude and orbit dynamics that is simulated. And so we can simulate the light that is reflected and is emitted from each one of the faces. And again, each face can be made of a patchwork of different materials. So we can simulate the light reflected and emitted from each one of the patches of materials on the surface of the object. We also implemented a high fidelity model, not just of diffusive light, but also of reflected light, because that was an important element that had to be accounted for, because, for example, in the case of solar arrays, from some angles, you have certain reflection, and that has to be accounted for when you then decompose the light of the object. And then we introduce in the model two different scenarios. One is when the sensor is in orbit, so there is no atmosphere, and the other one is when the sensor is on ground. So you're observing the object using a telescope, and there is the atmosphere in the middle. So the atmosphere is attenuating some of the emitted light from the object. We use the facilities that a Fraunhofer has here in Glasgow to validate the model. One thing that we did, for example, was to put in front of a hyperspectral imager real aluminum foil that is a little bit, it's not very flat, it's a little bit rough. And then we implemented a roughening function also for the surface of the satellites in our simulation model, so that we can try to mimic this effect, which gives a very interesting signature when you try to read it. And depending on the level of roughening, we have a curve that sort of match pretty well the measurements that we have in the lab at the moment. And the interesting thing that then we did was to simulate, again, objects. So you see here, for example, a cube that has different materials on each face. So here we distributed unevenly aluminum, gold foils, and solar arrays. And then we did spectral decomposition. So you have on the left the actual spectra. Then we do automatic N members decomposition of the light, and we do it in spectrum range. But then also because the object is rotating, we can deduce from there the relative abundance of materials of each face that is pointing towards the camera at each instant of time. And then taking from a library the spectral of the materials, we can say, well, so at this point, we have the solar arrays that are pointing towards us. And then in this case, there is another surface that is pointing towards us, and so on and so forth. The added feature that we implemented recently is an automatic N member analysis that use a white noise sort of filtering that is allowing us to, from multiple observations of the same object, to extract the dimensionality of the spectrum that we are receiving. And so we can automatically extract the number of N members, which is very important, because if you underestimate the number of N members when you do the spectral decomposition, you end up having the spectra that superimpose. And if you overestimate, then you have a lot of shadow signals. So you have curves that are doubling, for example. And the material association becomes a little bit more difficult. Then we have this association of materials that as explained before. The caveat that we realized when we did experiments in the lab is that if the material is not, say, as it is in the library, so it's a bit weird, or if there is a problem with the material, there's a deposition of something on the material, then the spectral signature doesn't correspond exactly. In fact, what could happen in space is that the material might degrade, and therefore the readings is not precisely as the one that you have in the library. So this is a caveat to the material association. But I think that is a promising technique to actually classify the object and also understand the motion. And in fact, we have a paper that we're going to present in 3 weeks at a conference in Madrid, in which we show also how we can understand the rotation motion. And we have a first attempt of associating materials to individual surfaces of an equivalent cube. So assuming that we don't know the shape at the beginning, but we can put that object inside the cube, we know more or less which material is associated to each one of the faces. And this is important because for tumbling objects, you might have one particular feature of the surface that is pointing the camera, and you might want to be able to detect that feature on the surface of the object. And that's me, and I'm open to questions.
Thank you very much, Max, for that very comprehensive talk. Have we got any questions in the audience? If so, please raise your hand. I think there's just comments in the chat so far. Okay, I'm not seeing anything come through. Might return if you're able to stick around, Max. We've got a period for further Q&A after the next couple of talks. So I think in the interest of sticking to time, we'll move on. But thank you very much again for joining us, and very, very excellent talk. So our next speaker is Hira Virdee from Lumi Space. So he'll be talking to us about the case for precision SSA. So do we have you with us, Hira?
I'm just going to check the audio in case we have feedback. Is that okay?
That sounds good to me.
Okay, I'll just switch my video on as well and share my screen.
Brilliant, thank you.
No worries. Let me know when you've got that.
That all looks good to me, ready to go.
Excellent, thanks so much. So I'm actually lucky to be here with our colleagues at the University of Durham today. And I left intentionally a bit of a vague title. I should have clarified that I wanted to present the case for commercial precision SSA, and I thought maybe some of our academic colleagues would have been put off. So what I'm calling for here is bringing commercial facilities and precision SSA into the mainstream. I realize in many ways I'm preaching to the choir, and apologies that this is much more high level compared to some of the talks today. Now, there's a lot of valuable and cutting edge research that we have seen today, but in reality, the space industry is becoming hugely commercialized. And in that context, current operational services are lacking. So as others have said, we need collaboration, but we also need productionalization. Now, I think there are a lot of things that have been agreed today. We've got known knowns like the amount of debris or the threat that it poses to sustainable space operations. ESA estimated that currently every collision avoidance maneuver in its planning and execution costs 25,000 euros. And that's without accounting for the downtime of the satellite. And this is a problem that goes as the order of n squared in terms of the number of objects versus the complexity of modeling the conjunctions and of dealing with collision avoidance maneuvers. We also have known unknowns. So we don't currently have precise positions, particularly of dead satellites. We don't have accurate collision probabilities. We don't have tumbling rates. We've got a lot of false positive warnings, and we don't have material properties or the origins of particular objects. And unfortunately, there's not a huge amount I can say about the unknown unknowns. So what do we get with satellite laser ranging? The precise information that we've seen in some of the recent talks reduces our uncertainty, our error bars, our covariance matrices. And currently, satellite operators are triple disincentivized in terms of their reasons to act sustainably. Firstly, they get a deluge of information that historically has been largely useless, this false positive set. These conjunction data messages, which simply aren't used because operators have been okay not using them. Secondly, we've got a lack of regulation, and whether that's governmental or insurance related, we've been talking about that for a long time, and I don't think we can necessarily put a timescale on when that will change. And thirdly, we've got, particularly for commercial operations, the downtime that's required in performing maneuvers, which distracts and detracts from commercial operations. So if we look at current ellipsoids based on radar, let's assume a 20 by 30 by 150 meter ellipsoid at the time of closest approach. An ESA paper recently highlighted an action threshold of 10 to the -4 to reduce the collision risk by 90%. And what that means is for each satellite that ESA operates, there would be 2 annual maneuvers per spacecraft on average, but a false alert rate of 99.9%, which in my mind is futility. If you already know that 99% of your actions are in vain, or 99% of your warnings are false, that doesn't lead to a whole lot of action, particularly for commercial operators. Now, comparing that ellipsoid to a 10 by 10 by 10 meter at closest approach, for the same risk reduction strategy, we have an action threshold 100 times larger, which means we need one maneuver per spacecraft every 40 years rather than 2 per year. And at the same time, that gives us a false alert rate of 10% rather than 99.9%. So we've seen lots of individual cases for precision SSA in a broader context, but what I'm calling for here is in very much a commercial context. So what's the real world impact that would have on commercial satellite operators? Based on numbers from Hugh Lewis in Southampton, we've got close approach. If we take a close approach of 5 kilometers, Starlink currently has 400 conjunctions per day. If we take a close approach within 1 kilometer, we have 15 conjunctions per day. So extrapolating that further, becoming more accurate, we reduce the number of conjunctions and we increase the actionability of those conjunctions. This graphic is to show the more than 5,000 orbital plane intersections that the future full Starlink constellation will have. So by reducing the error on the number of conjunctions, we increase the actionability of these insights. And a related point on that is the orbit carrying capacity. So as we increase the precision of data that we can gather, we increase the safe operating capacity for low Earth orbit. And in a world with 10,000 satellites expanding to, if we believe the plans or if they come to fruition, hundreds of thousands of satellites, precision information is absolutely vital, but in an operational rather than in a research context. And that really is the key to collaboration between academia and industry. Another graph, if anyone's been on the Astria conjunction streaming demo, precision information needs to be more widespread. So for example, we need more retroreflectors on board satellites, but we also need to operationalize laser ranging to debris. Because as we see in these charts, the majority of conjunctions in space are debris on debris. And whilst there's not currently a lot that we can do about that, it builds a much better case to leverage investment, to leverage further growth in that area. And what do we do once we have the precise information? It serves as improved initial conditions for precise propagation. So having the information right now has its uses, but we need that information to be more timely and to extend further out into the future. We've got, for one of the orbit propagation algorithms that's developed at UCL, through higher fidelity modeling, through improving force and torque modeling capabilities, along with the precise initial conditions, that improves our future predictions and knowledge, which is what goes into sustainable operations. And where does this fit into the broader industry? A hybrid data fusion approach is key. The problem we've identified at Lumi is a lack of this data gathering capability on the precision side. Another problem is the siloed and firewalled nature that has historically blocked collaboration. And I don't think that's one that will be overcome in significant parts because of the dual use nature of some of these technologies. But the former, the gathering of additional data, is something we can definitely work on. We have a growing team at Lumi working on this particular problem, and it's convenient that that's exactly what we're building. We've gone from TRL1 to 5 or 6 in less than 2 years. And we've got a growing team with key expertise across many of these technical areas. And then we've got the future applications of such a service. We've got the analysis of tumbling rates, important in rendezvous, tracking, docking. We've got low thrust, long-term propulsions, because orbit raising and several propulsion companies have proposed what are effectively non-Keplerian orbits. and the current mechanisms aren't in place to track those sufficiently. We've got improved conjunction warnings, characterization, mapping, and payload identification. Don't know why my slides don't come through entirely here. There was another graphic there, but SLR, as shown by Tom a few presentations ago, there are unique applications in determining the spin rate and axis, which is crucial to in-orbit servicing and manufacturing, active debris removal, rendezvous and proximity operations. And there are also applications in re-entry analysis by improving our models of non-conservative forces and how those vary as satellites tumble. So all that's to say, at Lumi, we want to enable and enhance the commercial application of precision SSA. And I've put a picture of Houssineau there because the UK has prominent research capability and outputs in this area, and we need to now extend that to industry. Thank you very much.
Thank you very much, Hira, and that's actually brought us vaguely back to the new timescale. So thank you very much for that. Are there any questions for Hira? I'm conscious, we're getting quite late in the day now, so we might move on to the next speaker if there's nothing else. I'm seeing nothing come through, and I don't think there's anything in the chat. So thank you very much again for joining us, and I'll move on to the next speaker now, who is Jan Siminski from ESA, and he'll be talking about orbit determination and attitude dynamics. So something that we've heard about each, and hopefully this will tie everything together and be quite a nice finish to the day. So over to you, Jan, if you're ready.
Thanks, James, and thanks also for this invitation to present our topics here. This is actually, I'm not going to present solutions, but actually research opportunities, so projects that are coming up from us and where we still need, in the end, people to apply and then performance research. The general framework is we have so-called TDE activities. These are activities that should raise the TRL from somewhere, let's say 1 and 2 to higher 3, 4, 5. And there's 2 currently open invitation to tenders. One is about robust orbit determination, a word that I just heard a few presentations back. And the other one is about semi-analytical attitude propagation. I'm going to explain why we find these topics important and what challenges or specific challenges should be tackled in this presentation. In this activities. So for the first one, I'd like to cite Gerhard Beutler from Bern University that compared orbit improvement and initial orbit determination to craftsmanship and fine arts. I've seen Thomas in the call, so I'm not sure if this is actually the perfect, let's say, citation, but this is from memory. And what we are after here is the orbit improvement. So in this case, the craftsmanship, because there's lots of construction sites. It's not, I mean, in theory, you have your orbit determination problem and you just use the least squares and adjust it and that's it. But in practice, there's many difficulties that need to be tackled. And the next slides, I'm going to show you which specifically we're interested in. The closing date for this activity is in end of April. So there's plenty of time still to submit a proposal. Now, the first point, or the first challenge about orbit determination is the update interval or the fit span. This is not the case if you use, let's say, a sequential filter, Kalman filter, which is just using updating the latest state. But if as soon as you take a batch approach, and typically for ground-based processing, and especially if you have less data, you can extract, let's say, by simultaneously looking at multiple observations, you can usually extract a better orbital estimate. But then you have the estimate of, the trade-off between increasing the amount of data in your batch, so increasing the fit span, and therefore increasing also the information that you can extract. But at the same time, your model gets less accurate over lower time span. So, okay, for a geo object, you might be able to accurately describe the motion over a month or so. But then for some LEO objects, it might only be suitable for a couple of days. And in let's say, practical cataloging systems, there are already some solutions that are proposed. So, for example, the most simple one is a lookup table. You use a quantity to describe somehow how much an object is, for example, affected by the atmosphere, like the energy dissipation rate, and then you just look up how long should my fit be. But this is, of course, not the most beautiful solution. And another solution, which would then would not require that you pre-compute this kind of values, but some kind of online optimization while you do your orbit determination. You somehow do this trade-off between how small are my residuals, how good is my covariance, and come up with a logic that gives you the best orbit. And another aspect which is commonly used is to augment or the force model with some kind of pseudo parameters and compensate for model insufficiencies. So for one classical example is that you basically estimate a ballistic coefficient once per day or once a certain time frame, let's say. By the way, the values in this table are just illustrative, just made up to show what was meant. The next problem, and that was already also discussed today, is covariance realism. We don't want to overestimate the covariance, because then our collision probability becomes less trustworthy. And we also don't want to underestimate it. So what one can do is one can simply compare this, let's say, predicted covariance against the history that we still maintain of our orbit predictions, and then you can compare, okay, what is actually the real errors that I do versus the one that we are predicting. And often we are overestimating the accuracy, especially during the orbit determination arc. And then once we propagate the atmosphere, the uncertainty due to the atmosphere is, of course, a major force. So how can you compensate that? One solution, which is also in current cataloging systems, is so-called covariance scaling, which is really a brute force approach, but okay, it works. But you can basically, from your history of orbits, you find a scaling parameter and then say, okay, now I just increase the covariance. Or you can calibrate this with a process noise. That this is, of course, only working for approaches with a Kalman filter or a batch Kalman filter, but not for least squares. Or you include consider parameters. And with this, then you can hopefully fine-tune your orbit determination in a way that the result is more realistic. And the next aspect that I want to highlight is the outliers and data association. Also, this was already mentioned today, the so-called cross-tagging that Toby Harris from Astroscale mentioned. So when we observe objects in very close vicinity, like, for example, when in this approaches, in this close proximity operations, or for some constellations, or after fragmentation events, it's really challenging to distinguish these objects, and you might only be able to distinguish them once they're separated enough. So in case of a fragmentation after a couple of days. And there are solutions, say, on the market, for example, multi-hypothesis filtering or probability density filters, but they become computationally expensive after a short amount of time. So if you have a lot of measurements and you don't have to maintain a lot of hypotheses, because you simply exclude the ones that become unlikely very quickly, then it's okay. So this is often used, for example, for the track formation and radar tracking. But then for the cataloging, I don't want to basically maintain one multi-hypothesis filter for thousands of objects, right? That somehow constantly cross-tagging with each other. So you need to find a logic that still keeps this in, let's say, manageable in terms of computational burden and also in terms of simplicity, but still being able to capture this possible multiple combinations. The other solution that is already also used quite often is so-called sigma filtering for outliers. So besides having another object that is very close to my, say, current focus, it could also simply be an outlier. And there you typically do you typically just cut off all the measurements that don't make sense within a certain band. And you have iterative approaches there. But these are kind of the baseline solutions that we're having now. And for the future, or for this activity, we are hoping for really like a framework that combines all of these into one clean solution. The last aspect about this orbit determination is data fusion. Right now, if you just take data from several different sensors and you manipulate the assumed uncertainty on the sensors, depending on the ratio between the two, you get completely different solutions, right? And then sensor might, if you calibrated your sensors correctly and you're now, let's say, confident with the uncertainty that you assume on the data, you might get good solutions, but the sensor could also spontaneously start to degrade in performance, and this should also be detected. So in the end, solutions for this kind of problems is trying to find consensus solution, removing sensors, adding them again, and change detection algorithms or inconsistency detection algorithms. So for this activity to finalize, we would like to have like a theory and a software prototype. This shouldn't start from scratch, but actually we have a high fidelity flight dynamics library developed by the flight dynamics teams in ESOC, which is called Godot, which is also has modern aspects like auto differentiation. So that can be used, and it also has an orbit determination tool that is validated and can be used, basically can be either extended or can be used as a reference. And then in the end, we have also measurement data, and we would like to have this demonstrated with real, but also simulated data, especially for very challenging situations like after fragmentation events, we don't have that much data. Now I come to the second activity, and also that was nicely introduced from Astroscale, which is the semi-analytical attitude propagation theory. And here we're thinking about really propagating the spacecraft attitude for longer time spans. So what was said, something like 2 years, or in order to allow active debris removal missions, or of course mission servicing. And the idea is that if you just simply now propagate a spacecraft attitude state over such a long duration, I can do this with the available tools. So it will take a couple of days of computation, and then I have a final state, which is completely not representative of what the final state could actually be, because it's could be a highly, let's say, chaotic situation where an initial change changes the output completely. So you have to do some kind of Monte Carlo analysis or some kind of other more detailed uncertainty treatment. And this is not possible if each individual propagation takes a couple of days. You end up sitting there for years just to do the simulation. So the first aspect of this activity is therefore to increase the runtime efficiency. It's clear this 6 degrees of freedom attitude propagators are slow. So typically have a very small integration step size, and that's actually also a problem, because if you integrate for a couple of years with a step size of a few seconds, you end up accumulating a lot of numerical rounding errors, and then this situation is anyway screwed up. The other aspect is that you have a very complex force model. So for example, you have to evaluate 3D spacecraft model with all the panels and all the components, and iterate through all of them in each time step. So that's a very time-consuming aspect. And there are some possible solutions. I must say there are not many. So this is not a topic that is well explored. So very low TRL, where you, for example, decouple the attitude motion from the orbital motion. You propagate them separately from each other, and then you use a closed form solution. So for example, you use a closed form solution to determine some kind of average area to mass ratio, and then use that for propagating it for a longer time, and then update the attitude again by let's say using the now propagated trajectory and so on. So that's one way of doing it, but I'm not saying this is the final way of doing it. As I said, it's low TRL. The other problem is we actually don't need the exact state in 2 years, right? Because it's in the end useless information. What we need is what also the companies need to remove the target. What is, for example, the rotation period? So in the end, what we need is proper, let's say, description of, let's say, proper variables that allow understanding the problem. So for example, as I said, the rotation period is one possible variable, but there might be also other variables that I could use, similar to what we use in orbit dynamics state dynamics, the mean orbital elements that allow you to efficiently, let's say, describe the mean long-term motion rather than focusing on where the satellite on the orbit exactly is, because that's also for if you propagate for, let's say, for example, 100 years, you don't mind, right? So, and with these variables, we then also hope that we can better constrain the uncertainty. So maybe while for the state itself it's chaotic, it could be in any direction. For the rotation period, if you're lucky, you can really say, okay, it's between A and B, and that's what then the company like Astroscale or any other could use to design their spacecraft to be able to in 2 years take down this piece of debris. Now, for modeling these uncertainties, that's also a challenging topic which we don't have usually in orbital dynamics. You can have this in highly eccentric cases or the special cases, but this chaotic motion where a very small initial perturbation leads to a completely different output in the end. There's other communities that have to deal with this problem, which is, for example, in weather prediction, which you see on the right side. And they use this kind of ensemble prediction, but also chaos indicators to show, okay, this is now let's say a possible outcome of this long-term propagation. So to conclude on this activity, here we're also looking for a theory and a software prototype. The focus is really runtime efficiency. So in case you go for a decoupling, also the orbit propagation needs to be fast, right? So we're thinking also about, let's say, having at least a semi-analytical orbit propagator in the back end to be able to really do this in a let's say, to really be able to tackle these uncertainties using, for example, Monte Carlo or this ensemble techniques. Again, the Godot library is existing as a baseline to do this development. So you don't have to start from scratch in the end. And also here we have already a historic real data of let's say collected light curves from several partners that are already presented today, but also from radar imaging. So that covers already a few years, and with this you can have at least a small set of comparison data. And with this, I conclude my presentation, and I'm open for any questions.
Thank you very much, Jan. It was a nice talk to round off the day. So I'm seeing Stuart with his hands up. If you'd like to take the floor, Stuart.
Yeah, thanks, Jan. That was interesting. I think some of the presentations we've had earlier today sort of underline the complexities that you were talking about, because you know, you talked about measuring the ballistic coefficient, but obviously anything that's tumbling, its effective ballistic coefficient is changing all the time. We've heard about, you know, the Yorp effect spinning things up and spinning them down, and the changes in the reflectivity of objects over time from Thomas that, you know, sort of implies that there are going to be accumulating changes in albedo that are going to affect the model as well. So, you know, I don't envy you the task of trying to, you know, sort of effectively represent all of those, you know, time variant elements to the problem, and wish you every success in trying to do so, to be honest.
Yeah, I mean, I don't think we have to model each and every aspect. It's normal to discard some effects. Like, for example, I would say for this application, the Yorp effect or the Jakowski effect is maybe not that important, because it's simply in terms when you compare it to the other components. And also, I mean, you have to compensate then with other tricks. Like I said, this ballistic coefficient, you estimate it in intervals, and then this is, I mean, internally in our flight dynamics, we call the ballistic coefficient the coefficient of ignorance, because it simply captures lots of other errors that you have in your model. There are tricks to deal with this situation and not being, let's say, setting up the fully perfect model, right?
Mm-hmm. Sure thing. Thank you.
Yeah.
Thank you, Stuart. We've also got a question from Thomas, I think, if you want to take the floor, Thomas.
Thanks. It's more a remark as well. I think one of the big unknowns we usually have is not so much just the modeling and precision and average, let's say, variables we're going to use. I mean, it is a big issue because of efficiency. I was mentioning the Jota tool. It's a nice tool, but it's very efficient because it takes a huge amount of CPU and time to propagate. But the other point is actually the a priori knowledge about the object itself. You know, if you're in low Earth orbit, for example, just to mention one important aspect is eddy currents. And in order to model eddy currents, you will need detailed information on the structure of the object, on the internal structure even. And we are missing that in all cases almost. The same with the angular momenta and things like that. So I think one big issue or one big unknown we have been encountering every time we try to model these objects was really not enough information to really, you know, apply the physics law properly. Thanks.
This is absolutely true. And actually, there's a component of this work as well that tries to fit, let's say, certain parameters to longer time spans of data, of observations, right? Because when we see a trend, we might be able to somehow describe it. And then, of course, the removal targets are often known objects. And then there's a, let's say, then there's also a way of modeling in the end the uncertainty by introducing, basically varying all these input parameters that are at least within certain ranges. But I agree, for some forces this might be more challenging than for others.
Yes, I think even the removal targets, you know, in many cases we don't know, even if you are the owner, like in case of some of these objects, you don't have the full information. So it's just a caveat, and I think Max is right, you know, and you're right as well. We can try to measure some of these parameters, and this is going to be okay probably for a propagation over a year or two. That depends on the environment and the type of object. But if it comes to something like propagating, just think of propagating the state of NVSAT over 10 years. Yes, I don't want to comment on that, but
yeah.
Thank you, Thomas. And another question from Duncan, I think, in the audience, if you want to take the floor.
Hi there. Yeah, this is actually an extension of Thomas's point. So in some situations of intact objects, such as satellites that had spun up momentum wheels, one of the initial conditions is, well, how big is that wheel and how fast is it running? And how long does it take for all of that energy to turn into body axes? And I presume the topics that you have been talking about, Jan, are ones where the assumption is that all of that energy has turned into body axes long ago. But, and I suppose this is the bigger point, this to me is a familiar theme because it comes down to information which could well be shared if its importance was understood. You know, information that could come from manufacturers.
Yeah. Okay, agreed. For I said for some parameters we can as said observe these rotation rates over a certain amount of time, and then fit damping parameters, for example, that are not necessarily then physical, but at least try to capture this to some degree. But of course, then also the let's say extrapolation becomes more challenging. And yes, I mean, at least now, I'd say we are at the stage where we still remove targets where the operator is cooperating, I would say. But as Thomas says, even there we have lots of uncertainties.
Yeah, sure. Thank you.
Mm-hmm.
Okay, thank you, everyone. And thank you very much again, Jan, for an excellent talk. We did have a brief period of discussion planned for right now. So just quickly opening the floor up to any questions or discussion points about any of the talks that have happened today. Now is the time to highlight them if you have them. Not seeing any hands. Duncan, is that a legacy hand, I think, from the last question? Yes. So if there's nothing else, I think we'll move on to the very final contribution of the day, which comes from Stuart Eves, our program manager. He's going to go into a bit more detail about some of the funding opportunities that I mentioned in the introduction, and also highlight some of the future program that we have coming up this year. So I'll hand over to you, Stuart, if you're ready.
I am. James, can you see and hear that?
Yeah, that looks good to me. Thank you.
Okay, thank you very much. So yeah, just quickly to finish, I just wanted to mention a few of the things that are coming up in the GNOSIS program. So on the 4th of May, we have an event talking about SSA in astronomy, an issue that has generated quite a lot of discussion and debate, including at the National Astronomy meeting last year. The points of contact for that event are the academics that lead the GNOSIS network, Bob Mann and Don Polacco. Then in June, we're going to be following up as we tend to do. We had in January a space-based SSA workshop, and in June we'll be following up with the more in-detail sandpit that we typically do. So if anybody on this call is interested in contributing to that event, I'd be very interested to hear from you. I already have 2 or 3 potential contributors in my crosshairs, so to speak. We're hoping to work with the Secure World Foundation on an event that's coming up on the 22nd and 23rd of June. I've included the web link on this slide and stolen the sort of picture from their website over on the right hand side of the screen. But if you're not aware, the Secure World Foundation has been working in the sort of area of space sustainability for some time, and we're hoping to do a joint event with them in June. On the 5th of October, we're planning a thing that we're entitling Black Swan events. So I'll talk a little more about those on a slide that's coming up in a moment, because you might conclude that Black Swans are sort of unpredicted events, and so how could you possibly have a debate about them in a workshop? But I'll explain that we're taking a slightly relaxed view of the definition of black swans. We're just talking about sort of unusual, unexpected, low probability events, really. And then in November, we'll be holding our annual conference, and our theme this year is space sustainability for the next decade and beyond. It'll be a sort of hybrid in-person and online event, and the point of contact is my colleague Dinsley for that one. And then we're hoping, although we haven't quite finalised the details yet, to hold another event in December looking at the careers in this area, and what sort of skill sets and opportunities exist for people in space sustainability. So I mentioned the Black Swan events. We've had a bit of a think, and we have some candidate topics which are listed on the screen here. I think we have room for some more. So if anybody's looking at this screen and saying, aha, you haven't thought of that, please do get in touch, and we'll potentially add some additional events to the list. But what we're trying to capture here is things that would make a significant difference to SSA, which might only happen very occasionally, but would actually make a very significant difference to the topic area that we're dealing with. So one or two of these things are, sort of things that have been predicted and discussed. I'm hoping that my friend Darren McKnight may accept an invitation to come and talk about the implications of collision between two large rocket bodies, which would involve a lot of mass. And when we talk about a major space weather event, we're not just talking about Carrington type events. There are events from the sort of historical record of even larger events than Carrington. So we're looking at trying to categorize and understand the effects of some of the really extreme things that might happen. I won't talk through all of these now, but you can see the sort of direction that we're trying to go, and hopefully you may find it quite a stimulating and diverse session when we hold it in October. This is just a reminder slide that we are have grant money available for ideas that members of the network come up with, and we've put out some particular technical challenges which are listed on the slide. Pleased to say that James and I had a discussion recently with a consortium that's potentially going to respond to one of these challenges, which is exciting. So we're very much hoping that we'll receive an application for some grant funding from them soon. Just as a reminder, we're anticipating sort of up to about 30K for these studies. So they're relatively short time scale, lasting a few months. The only constraint really, because of the way that GNOSIS is funded, is that there should be a STFC-led application for the funding. This is also just a reminder slide that we have GNOSIS studentship money available for support for PhD projects. Again, pleased to report that we've had some dialogue recently and are expecting another PhD application for this funding, which we're again excited about. So that's another area of GNOSIS activity that's moving forward. So we're in a position to part fund PhDs, and if anybody on the call is thinking about doing something, do please get in touch for further details on the website. This is how to find it. Go to the GNOSIS homepage, and then as I've indicated with the yellow ring, there's a funding tab. If you have a look at there, there's a very simple expression of interest form, which is not much more than telling us your name and telling us your email address so that we can get in touch with you, and then a very simple form to submit proposals. So it's a pretty streamlined and straightforward process, we hope. So just to finish, an invitation: if you've seen anything on the screen in the last couple of minutes that you think is interesting, please do get in touch with me or the other members of the network. If you're not already a member of the GNOSIS network, please do sign up for our regular newsletter on the website, or you can follow us on Twitter. And that concludes all I had to say. So unless there are any questions, I'll hand back to James to wrap up. Thank you very much.
Thanks for that, Stuart. And yeah, it's nice to have everything about the funding and future programme in one place. Hopefully we'll get some interesting ideas sparking from this event. I know there's been an excellent programme today. But yes, as Stuart says, that brings us to the close of today's programme. So just to make sure that there are no questions, are there any questions for Stuart or indeed any of the speakers that may still be on the line? I don't see anything. And yes, just to reiterate that the recording from today will be available. We'll be distributing the link shortly, probably in the next couple of days, along with the feedback form that Teresa mentioned in the chat. So yes, we very much value your feedback about not just the event, but what we're doing at GNOSIS in general. And yes, please do take the time to fill that in and let us know your views. But with that, I'll bring today to a close. Thank all the speakers again for their contributions, and thank you to all of you for sticking around for such a long afternoon of talks and discussion. So thank you, and goodbye.